slide. Good morning, buenos días, and welcome to this first scientific meeting on trends of power electronics organized by Mondragon Unibertsitatea. Thank you everyone for coming to our place. Hello also to those that are following the event online. I hope we all make the most of this event today. To start the day, and before getting into more details about the event, I will give the floor to Roberto Uribe-Echeverria, the Research, Development, and Innovation Coordinator of Engineering Faculty of Mondragon Unibertsitatea.
Thank you very much, Mikel. Well, it's a pleasure to see so many people here. So they told me it's about 100 people and another 100 online. So welcome to everybody to this first meeting, as Mikel said before, and ongi etorria denoi. Batez ere oraino etorri zaretenoi, eta ongi etorria baita ere online jarraituko duzuen guztioi. I don't know if you have ever heard the word permacrisis. This has been in the news for the last year at least, and for me it was a word that I learned in the UK news, and it means that, well, it was related mainly to Brexit and the Tory party, but apart from that, it means that we are actually currently living in a permanent crisis, right? And in fact, this was the word of the year for the UK in 2022. And permacrisis also can refer to a permanent crisis that we're living nowadays, as I said, and the current socioeconomic situation with a war next door, fuel shortage, and especially climate crisis, makes energy crisis one of the main part of this permacrisis I have been mentioning so far. Okay. But some claim that crisis is not necessarily awful, okay? And some way, in long term especially, crisis prove a necessary and beneficial corrective that boosts technological progress as well. So being in a crisis may mean that we get on faster, more clever, and try to do things better. And I hope that this crisis also lead us in the right direction in that sense. Okay, in the energy scenario, new technologies must be developed for generation, conversion and transformation, transmission and energy storage. Okay, and that's where we can find power electronics as a key element to maximize and optimize the available resources in the middle of this uncertainty we are living nowadays. The Basque Country is also a lead actor in power electronics. We have several strong manufacturers that are competing globally with the world best-in-class industry, such as Ingeteam, CAF, Orona, Gamesa, Ormazabal, Gema, Fagor. I am mentioning a few of them. I'm probably missing many of you as well, so sorry about that if that's the case. But the Basque Country is a really strong region in power electronics as well. Not only because we have industry, but because we also have a research center like Tenalia, Ikerlan, CEIT, so on and so forth, and universities. All the Basque universities and also the Navarra Public University, CEIT, Mondragon University, and EHU, and UPNA. We all have strong research groups devoted to power electronics. Okay, and together we made the Basque Country a major player in this league as well. Okay, so all of us together, together with other international colleagues, we must face the challenges of the energy transition from generation to applications such as electromobility or nowadays so popular hydrogen technologies included. Okay, I really believe that Mondragon University is a true reference in power electronics too. Okay, our electric energy research groups has been working for many years now, especially in three main topics, which are the drive systems, energy storage, and also power electronics again. Okay, this is a very big team, a great team, composed by over 40 researchers, 30 of them with holding a PhD, another 15 or more PhD students, and they have traditionally worked with the local industry, with many of the ones I mentioned before, in the Basque Country, many times, most of the times under contractual research contracts, but also under public funded programs such as European or regional programs, but always related to industry. And we always, this is one of our main characteristics of Mondragon University. Our research groups are very close to industry and work generating new knowledge, but focused knowledge to try to solve real world problems. Okay. Nowadays, we have also obtained international projection, and as well, we are currently collaborating with other partners such as UNIZAR, VUB, Infineon, Denso, or Speakboat that are internationally well known as well. This is a team, our electric energy team, with a bright history, as I mentioned, but even a brighter present and a brighter future that will contribute to mitigate this energy crisis, as we've been talking from the beginning. Okay, thank you very much again for attending this meeting. I'm sure that it will be a very valuable event with many fruitful discussions. Besterik ez nire aldetik, Mikel, ongi etorri berriro ere, eta ekitaldia aberasgarria izango delakoan, urren arte. Mila esker.
Okay, thank you, Roberto, for your words. Well, as he said, we are in a situation with this crisis, this energy transition, and well, there are several challenges to face regarding this energy transition. The power electronics will be key for success in this journey. There are many different approaches to improve key indicators such as efficiency, cost, overall performance, and well, we are covering some of them today. Okay. For example, the improved semiconductor materials. Okay. Until recently, most of the available semiconductors of power electronics were based on silicon. The industry has evolved until reaching to fully exploit the physical limitations of the silicon. New wide bandgap materials, such as silicon carbide and gallium nitride, will provide a further improvement in terms of efficiency and performance. You will see today how these new wide bandgap materials are key in the latest research works in power electronics. You will see today, although there are still challenges to overcome in the integration. Okay. Another approach toward this optimization stands on the converter topologies and architectures. Traditional or classical power converters, both in DC-DC applications, DC-AC applications, are being step by step, little by little, substituted by alternative topologies. Partial power converters that will be introduced later by John Anzola, are a clear example of these alternative architectures. Finally, we shouldn't forget the role of the passive devices. The maturity that power semiconductors and power converters are reaching make in some certain applications the passive devices the limiting element in the conversion system. So this is also a challenge that we must tackle. Okay? We are, as I told you, we are today discussing some of these advances and challenges. Okay, thanks to the international renowned experts that are here with us to introduce them. Okay, so Professor Tolbert from University of Tennessee, Knoxville, will talk today about a test bench based on power electronics that allows the emulation of grid utility. Okay, Professor Subhasis Bhattacharya from North Carolina State University will speak about the solid state transformers, and he will introduce a newly power power device, power switching device, a bidirectional power switching device based on silicon. Okay. Professor Michael Andersen from Technical University of Denmark will talk about his research in the switch mode audio amplifiers based on gallium nitride. Okay. Later, my colleagues Igor Baraya, Chaburu, and Yusuf Puru will talk about the past, present, and future trends in power electronics, especially from the point of view of Mondragon Unibertsitatea. Finally, our brand new doctors will explain some of the recent research work. Dr. Anchon Arrizabalaga will talk about the challenges in the integration of silicon carbide devices in high power electronics. And finally, Dr. John Anzola, as I told you, will introduce the partial power concept. Okay. So as you can see in the timetable today, we will have 3 main sessions. We will divide the event in 3 main sessions. We will have 2 breaks between them. As I told you, we will have some on-site attendees here, other attendees online. We will try to answer all the questions. We will ask our experts different questions. We will try to answer them as much as possible, given the tight schedule we have. Okay. For those that are connected online, you can ask the questions through the chat. We will have our colleague Eneko there trying to handle all the questions, and as I told you, we will try to answer all of them. Okay. The following days, you will receive a message with the content of the presentations of our experts today. Okay. So without losing any more time, I will introduce the first speaker today. Okay. Yeah, sorry. I don't know if they have done. Is it working? Okay. So I will start introducing Professor Tolbert. Okay. The first talk this morning is titled Electric Utility Grids, Large and Small, Emulation through Power Electronics. It's in charge of Professor Leon Tolbert from University of Tennessee, Knoxville. Leon Tolbert received the Bachelor, Master Science, and PhD degrees in Electrical Engineering from Georgia Tech. He worked at Oak Ridge National Laboratory, Tennessee, from 1991 until 2020 on electric distribution and power quality projects. He joined the University of Tennessee in 1999, and he's currently a Chancellor's Professor and the Min H. Kao Professor in Electrical Engineering and Computer Science. He's a founding member of the National Science Foundation Department of Energy Engineering Research Center, CURRENT, which develops technology for the future electric grid to accommodate a high penetration of renewables. Dr. Tolbert is a fellow of the IEEE and a registered professional engineer in the state of Tennessee. He's the deputy editor-in-chief of the IEEE Power Electronics magazine and the publication chair of the IEEE Industry Applications Society. He was the recipient of the 2001 IEEE Industry Applications Society Outstanding Young Member Award and 8 prize paper awards from the IEEE Industry Applications Society and Power Electronics Society. He conducts research in utility application of power electronics, including microgrids, interface with renewable energy sources, medium voltage multi-level converters, and the application of wide bandgap power electronics. Please, Professor Tolbert, the floor is yours.
Good morning, buenos dias. Very appreciative that Mondragon University invited me here this week and to participate in PhD defense and today, and really have enjoyed my week in the Basque Country. So today I want to introduce some work that we're doing at our university related to the emulation of electric grids, but using power electronics, and you'll see why I use the word emulation and what exactly that means. But first, I'm going to introduce our university quickly. Our department has about 50 faculty and more than 1,000 undergrads and 250 graduate students. And then within that, we have Current, which is a research center looking at the future electric grid. We also have a project called Potential, and I'll talk a little more about that, a traineeship for students. And then Oak Ridge National Laboratory is a Department of Energy laboratory nearby that does work, I say, on everything. And so we have close collaboration with them as well. And there's some websites there for people who are interested in getting more information about each of those. So Current, our vision is really to look at the grid when you have high penetration of renewables. And when I say high penetration, something like 50% renewable energy, 80% renewable energy. And in the US right now, we're at about 10% if you look at just solar and wind, but we're growing 1% per year. So that's changing very quickly. So it won't be long till we have these high penetration levels, and certainly some states already do. And of course, as a university, our main goal is to produce leaders as well. But a lot of our renewable energy is here in the middle part of the United States, but people tend to live here and here. Our current members, we are 4 universities, including University of Tennessee. We also have Northeastern, Tuskegee, Rensselaer. And then we have 35 approximately industry members. Several of these are large utilities like Dominion Energy, Peak, TVA, Southern Company, New York Power Authority. And then we also have several companies that I think many of you know, companies like Danfoss and Boeing and Hitachi, Eaton, Keysight, General Electric. And then also proud we have several national laboratories that are members, as well as Electric Power Research Institute and National Rural Electric Co-op Association. So I think we have a good group that are members. And then in power electronics, we have 5 full-time faculty. You can see their names there, Daniel Costanet, Fred Wong, myself, Kevin Bai, and Helen Sway. We have about 35 grad students in power electronics right now, and Current has about double that. So we also have 5 faculty in power systems and just about as many in students in power systems too. And I think one of the unique things about our university is the power electronics, power systems professors do have a lot of joint projects. And we also do a lot in terms of trying to have students doing hands-on work in the laboratory. Here's a classroom where they're building controllers for electric bicycles. So I mentioned this wide bandgap power electronics graduate traineeship that was funded by DOE. You can see some of the classes of students that were part of that. It was started in 2016. Virginia Tech and our university were awarded these, and it was to try to, again, increase the number of students who have experience with wide bandgap, because they recognize that that's going to be needed. And so we developed a lot of new courses. Several of those courses are available online if you go to this website, meaning the course materials are there and ready to be adopted or used at other places. Our facilities, our building was built in 2012, and we got our research center actually a year before that. So the nice thing was there was a large area where they were able to build out our power electronics lab. So we have a very large low and medium power laboratory. We have the grid emulation lab that I'll talk about today. Visualization, we have a high power lab that's kind of being finalized. And so we can do work up to about 1 megawatt and 40 kilovolts. We've also done high temperature testing and at cryogenic, minus 200 degrees C. So this kind of shows all the research applications that power electronics can be found in. And we do research in many of these areas. I know Dr. Castanet has done some work on medical devices. We've all done some work in power supplies, trying to make those more efficient and more compact. Quite a bit of work, as I mentioned, in renewables and integrating those with the grid and other utility applications. I'll talk more about these today, and also microgrid. Wireless charging, have done quite a bit of work for whether it's consumer electronics or electric vehicle, and then quite a bit with aerospace, again, trying to make things lighter, more compact. So as I mentioned, our renewable resource, if you want to call it, at least for wind, is mostly here in the middle of the United States is the best wind resources, and then a little bit along the coasts, but we don't have many people live there. You can see the density of population is pretty low. So it's good, you can put lots of wind farms, you're not going to bother a lot of people, but you got to get that power from here to here or here to here. Same thing, the best solar is here in the desert Southwest, and need to get that power to this coast or here. And so our center, at least initially, was looking at how can we do that from a transmission level. And so some of the ideas there are to build something like a multi-terminal high voltage DC overlay. We have a couple of existing DC lines in the United States. But we are going to need more of that if we're going to be moving large power long distances. Also, we're going to have to be able to accommodate not just variability in the load like today, but that variability in the generation, because as everyone knows, the wind is changing, sunlight is diurnal and changing daily. So storage is going to be very important. Responsive load, meaning can you just turn off the HVAC for a few minutes to kind of help balance things out, or electric vehicle charging, can you kind of schedule that and make that better? So we're trying to model this future electric grid by doing that in hardware with power electronics, and I will explain how we do that. The United States electric grid is actually 3 electric grids: the East, the West, and Texas. Texas always a bit independent, kind of like the Basque Country. They have their own grid, and you think, well, there's 3 grids and there has to be connections. There is, but they're very weak. And so actually the frequency of these 3 grids is not the same. They're all 60 hertz, but they're not synchronized. So one of the ideas then was to put an HVDC overlay on top to link East with Texas, West with Texas, East with West. There's already this 2 to 6 HVDC, and this is existing, a tie between Canada, Hydro-Quebec, and the New England, New York area. But we're saying maybe it would be good to add something like this to help accommodate this high penetration of renewables. So we'll show the work we did related to that. So an electric grid has lots of generation sources, something like G1, G2, perhaps loads, various loads. We can represent that with power electronics and just basically control this converter to act like a generator. Maybe this one to act like a second generator, this one to act like a load. So power would flow out. You see the current arrows out here that flow back in for this load. And this back DC bus just kind of helps to provide power to it. And so this might represent a single bus or a cluster, kind of an aggregated generation and load center. And so this is showing what I was talking about, where we have generator where the power is flowing out. We have storage, it can flow either direction, bidirectional. Load, it's flowing this way. And then we just have this back DC bus. This is basically what we're trying to emulate is the AC grid itself. And so we're really more interested what's happening over here. The DC, it just makes up the losses in the system. So you can represent a fairly high power system and not actually need a lot of power from your building. We also have a pretty nice control room, visualization room, where we can see everything that's going on. We try to control it like each is a separate control area so that it's similar to a control room in a utility. It's of course not the same, but some of the same functionality where you can monitor voltages and currents, frequency, and see what's happening. Of course, this needs to be reconfigurable because you want to perhaps not just look at the national grid, you may want to look at a different portion. And so we're able to switch out inductors to represent the line impedance. We also can take two converters back to back, as I'll talk about in a second, and let that represent an impedance. So we have different cabinets. We've got cabinets here to represent variable inductance. We've got back-to-back converters, which could represent, again, an AC line, or it could represent a DC line too, and have that in our system as well. The system control architecture, a very busy slide, I call it, quite a lot on here. But there's a lot going on in our electric grid, which if you're not a power systems person, you may not realize all the computational complexity that's going on in the background. And so from power electronics, we're usually more thinking about things down here like maximum power point tracking of your wind or solar. Perhaps we're going to do inertia emulation and droop control and some other things. Load, I mentioned we need to be able to represent that, but also do demand response and load shed. Generator. But up here, you know, there's a lot going on in terms of state prediction, in terms of doing our automatic generator control, unit commitment, our power flow calculation, stability, contingency rankings, just, I say a lot. And so that's, I think, also unique is that we're trying to incorporate all of this in our emulator, and we're not trying to leave things out. And so a lot of times that interaction of these different controls causes some complexity or things that maybe you don't see it if it's just a simulation. And so that's why we call it more of an emulation, because we actually have power flow. So we want to demonstrate several different things using our system. And I'm going to show you here in just a second where we're looking at, you know, perhaps being able to move power over longer distances, or looking at regional control center and things that are going on in a smaller area too. We develop many different emulators, and these are basically equation-based to represent synchronous generator, to represent things like different loads. And the load could be zip load, meaning constant impedance, constant current, constant power, or it could be something like an induction motor. It could be lighting. It could be electric vehicle charger, data center. We can represent all of these in our system. Wind, we've looked at type 3, type 4. Solar, look at the solar with converter, transmission line. Storage, we've looked at battery, flywheel, doing ultra capacitor or super capacitors now. And then the HVDC. We also can do faults on our system, which is very important, of course. I always say everything runs well when everything is running well. But our grid, you have to be able to accommodate loss of a transmission line, loss of a generator. And so we spend a lot of time looking at these different faults and scenarios. So our solar power emulator, again, we can represent something that looks like this: PV, a DC-DC boost converter, inverter, output filter, represent it all as just an inverter with some output inductance. Just basically programming it to behave as it would this system, so that the output current and voltage looks like what we would expect from a system here. This is showing different irradiance values, like 1,000 watts per meter squared, 600, 800. And you can see the current is going to go up when the power goes up, and then it's going to go down when there's less irradiance. And so that's going to be changing just as the irradiance changes. And so we can then also do all of these different control strategies and try to figure out what is really needed when you have these high penetration levels. Do you need more reserve power? How much reactive power control do you need? How are you going to ride through low voltage? This has become very important in the United States. They've had faults on system remotely that drops the voltage, and then all of the PV drops off. And suddenly you just don't have enough generation to supply your load. And so they're needing better ride-through capability with PV inverters. Wind turbine, we can do very similar. Again, a full converter where you have your usually permanent magnet generator, or it could be induction generator here. And then you have a rectifier, and then you have your inverter to put it on the grid. We can represent that also here and look at different control strategies, different wind turbine models. And so this incorporates, these physical models and control strategies. And we're able then to hopefully produce waveforms that, as our wind speed is changing 9, 12, 10 meters per second, that current is, going up higher wind speed or going down at lower wind speed, and be able to represent that. I mentioned energy storage. Again, it looked very similar to our PV, except we have a battery here and still have in this case, a bidirectional inverter, but also incorporate some different control like inertia emulation. Try to inject power when it's needed, similar to a synchronous generator. Also need the ability to provide reactive power to help regulate voltage, and able to, again, look at different scenarios. And this is showing one where with inertia emulation, we're able to keep the frequency closer to 60 hertz, whereas without it, you can see there was an overshoot and weren't able to regulate frequency as tight as we would like to. Aggregated variable speed drive. I think, as most of you know, variable speed drive is becoming more and more important in industry because it's so efficient, and you're able to, in processes, control the speed of your motor load better. We've also said it's important to be able to use it when you have loss of generation. There are certain loads, some pumps and fans, maybe it's not so important that they're precise, and you can lower that load and help regulate the frequency of the grid with your load, not just your generation. And so we've come up with a way to do that, and to try to do that in an aggregated sense, and look at that from a regional sense. Data center is another load that's increasing. Again, it typically has some front-end power electronics that takes the AC, converts it down to a bit lower AC, and then it goes to DC. And, this goes from a fairly high voltage, it could be 480 volts or even higher, down to the processor level, which is typically 1 volt DC. Not all that efficient, but we're able to do all of that and again, represent it with just a converter, and be able then to look and see when there's a change in the AC voltage, how does that impact this voltage? Because we need to keep this voltage at 1 volt so that your computers are still processing their data. So here, this is showing a voltage sag and showing that it was long enough that we had to switch over to our battery to get that voltage back up, and so able to maintain that. Also, we're able to represent, again, these power electronics here. You can control that to provide reactive power support to the grid. And so you keep seeing this theme of, I call dual use, not just use it to provide power to our load, but we can also use it to help the grid a little bit. I mentioned be able to do a short circuit. You may wonder, well, how do you do that? You just go out and throw a wrench on it and cause a short circuit? No, we have to be a little more careful than that, but we can control the voltage to go to 0 right at that bus, and that's the same as a short circuit. And if we start out at a low enough current, since we're doing everything in per unit, if we start out at 5 amps and then our short, the current goes to 50 amps, well, that's still within the rating of our system. And so we are able to do something where basically show that the voltage here goes very low when you have a ground, and the current goes very high during that short circuit. It's still within the rating of our system, but we're able to represent that in our system and reflect what's happening, and then take some action to try to isolate that short and make sure things can ride through. Our transmission line emulator, this took, I say, several years to get this to work kind of the way we wanted to. It's just 2 converters back to back, and we're just wanting to regulate the impedance across that line. And that represents how much power can be transferred across that line. And so it's pretty easy to represent something like, this shows 2 parallel lines. Well, if you have a fault and one opens, your impedance doubles because you only have 1 line. We also can represent how that impedance changes when there is a fault, kind of at some intermediate point. And I think that also helps us. We've also been able to do some different fax applications using the same emulator. So one of the things that I think everybody knows is increasing quickly is offshore wind. One of the ways to get that wind power from offshore to onshore, offshore would be here. This is representing the New England area and New York and Boston. To get that power onshore is to use multi-terminal HVDC. The nice thing with multi-terminal is if you do lose a converter, you may lose the input from this wind farm, but you can at least still this wind farm bring the power in. Or if you lose a single transmission line, you have other routes to get the power in. And so we did 2 or 3 things with this system. One of them was to look at something like inertia emulation and be able to, typically our wind runs at maximum power point tracking, but if you have a fault or loss of generation, you can see our frequency goes pretty low if you're doing MPPT. You can't, it's kind of the worst case. If you can do some inertia emulation, meaning you're not quite doing MPPT, your frequency is not going to go as deep. Your net frequency nadir is not as deep. You could also do more of a voltage mode, which is not quite as bad, but not that great either. If you can incorporate a little bit of storage in addition to your wind, I'm not talking about a, storage for hours. I'm talking about storage for seconds. Then you can keep that frequency dip to be about the same as what you would see with traditional synchronous generator. And so I do think we're going to have to do a lot looking at how much storage do you need? Do you really need it for hours, or do you need it for minutes? Do you need it for seconds? In many cases, you don't need hours necessarily. Wide area damping. Sometimes there are faults or other things in the system that cause oscillations. And typically those kind of just on their own damp out. And this is showing even without control in the blue, it damps out after just a few seconds. But we developed an algorithm where you're controlling your generator and or your inverters to dampen it so that it comes down more quickly and doesn't cause some sort of issue, excite a resonance somewhere. What was interesting was the students did this in simulation first, and it worked great. It looked just like this figure. And we said, okay, let's try it on the hardware test bed. So we went and did it on our hardware test bed. It didn't work at all. It just made it worse, their controls. Well, what's the issue? Well, there were some time delays and things that are happening in your system that they were not taking into account in the simulation, but exist in your real system. And so once they built in those time delays that occur in your controls, and they're not long time delays, actually, just fairly short. But once they built those in, then it worked like what we expected. And so that's what I like in our system, is it's real power flow, real converters. It runs in real time. And everything has to run in real time, just like the grid of today. This is another one representing, again, the offshore wind, but a large load increase. But then showing, eventually as that load increase, that typically it's going to collapse. So we had a professor do a stability margin prediction and kind of represent what that stability margin was going to be. And basically predicted that when that margin is zero, meaning you have no margin, things collapse. And you see that things here start to fall off. But also said, okay, we don't want it to collapse. Why don't we do some reactive power to help control that voltage? And so when that margin got to be a little bit too tight, we let our reactive power support kick in and keep a margin like 0.15 per unit margin. And we're able to then just continue running, not collapse. So this measurement-based voltage stability was something we also demonstrated. So another grid we looked at was the Western US, looking at basically several nodes here. We did add a couple of HVDC lines that are not existing today to help us as we have more PV, more wind, and we think that's going to help maintain the stability of this Western grid. And again, be able to represent this green triangle or multi-terminal HVDC is shown here. And again, we did several different scenarios. One of these was to kind of predict basically what's happening in our system, and then be able to take an action if we have a fault. Our Western grid is not as firm or stable as our Eastern grid. And if you lose one of these transmission lines, a large one, things can go unstable. And that's what this is kind of showing here, that if you don't take any control, you can see the purple things I call get out of hand pretty quickly. The frequency is not very good. But if we know that, okay, we've got an issue and we can take some action or control, we can bring that frequency back to 60 hertz, like we would want to. One of these actions is actually, we have to separate the grid and actually trip these lines and separate into a north and a south. And that's able to maintain stability instead of trying to send power over long distances. So this is showing one of these issues where we are representing our wind and we're changing our controller, and you're going to see we end up getting harmonics here and having oscillations because it just, our controls were not good, and then we can tune it and get it to come back and get it where it's supposed to be. So again, it's a way you can look at some of your controls and be able to tune those. Another scenario we've been looking at, especially in California, is in the evening, they have very good solar resources. They have a lot of solar installation. But of course, during that evening time, your renewables are going to start to decrease as we get late in the afternoon. But our load is going to go up when people get home, turn on their air conditioning, start their cooking. And so it's not a good time of day when your load is going up, your renewables or your solar is going down. And so they found an issue there. So we've also looked at that. This is showing the national grid and being able to look at some different contingency cases. And this is calculating all these different contingencies online so that we're aware and can take some action, hopefully, before something happens. This is showing this running. The red means it's running. You can see things are changing slowly. We can see there was an issue with the voltage here, so we highlighted it and put up a warning. We took some action. It was okay, went back to green. And then just continue to look at different contingencies, and there's going to be another where there's a trip, as we'll see here in just a second. And it's going to, something that we couldn't do anything about. We lost something here. These lines then tripped, and we were able to go back. So we use this system not just for something very big like our national grid, but we also can use it for something small like a microgrid. And we've done a lot of work with microgrids and developing controllers. And we had a neat project with Chattanooga Airport. They had solar. They wanted continuous power. We developed a controller for them and tested on our system before we ever try it out on the utility grid. So it was pretty advanced and ready to go. We didn't have to do a lot of tuning once we put it on their system. And we did something for what's called dynamic boundary, meaning if we have a lot of solar, we can provide power to a larger area. If we don't have much solar or energy, we just provide power to the airport. We don't try to provide it to everybody. And so we were able to do this dynamic boundary of changing how much area you serve as the generation and load changes. And of course, the big issue there is this active reactive power balance and having to calculate that in real time, all the time, and kind of have an idea of how much generation and storage you have, what the load is, and try to project that out for a few minutes and just have that running continuously. Also, protection. You have to be able to identify a fault. If there's a fault on our microgrid, you have to isolate that, of course. And so you have to be able to, with your relays, open that, isolate your fault, provide power to the airport, but not provide power to your fault. So we also had to develop protection system that runs in real time and do that as well. So this is showing this, and I call it, it's a bad day. Lots and lots of faults. This is running at 4x speed, but you'll see there's a fault, there's isolation here. We clear the fault, we can provide load again. Oh, another fault. We have to open, shrink the boundary. It becomes a permanent fault. This turns off. But we have enough solar. We could provide more power. We had another fault. Like I said, just a bad day. But we're able to test all of this and run this in real time. Again, just different faults are occurring. Finally, all of our faults are going to be cleared. And we're going to start to try to resynchronize. And if you see this grid voltage, this voltage has to synchronize. When they do, this can close. So what I showed you there ran for about 1 minute, but it actually took about 4 or 5 minutes for all that to occur. So some of the advantages of our hardware test bed is it runs in real time. You can do real power flow, lots of inverters having to run in parallel. So it's a lot more representative of the real system. I don't have up here disadvantages, but disadvantages are also, it's a lot of work to build a system like that. And it's not as easy as a simulation, of course. And it's not as easy to change and look at different systems. So we're hoping to have another project where we can get one that's even more easily reconfigurable in the future here. So again, just wanted to thank at least NSF and DOE are the ones that sponsored us. And this is showing several of the companies that helped us with this project. And thank you, and take any questions.
Is there any question in the audience? Yeah.
Hello, thank you for your presentation. It was very interesting. I am very impressed with all the setup that you have presented us. I could make many questions, but one question, maybe in one of the slides, you have shown that you are emulating interaction between converters, yeah? And then you have shown that you solve a problem of perturbations and so on. But my question was, how do you tune the controllers? Which criteria do you use to tune the controllers? Maybe more than one, but could you comment on that, please?
Yeah, certainly we didn't show a lot of the detail that went into. There was a lot of work in getting this system to work initially, meaning we actually had to synchronize the PWM of all of these converters, just literally switching at the same instances. And then we also had to look at trying to do a lot of the tuning of the KPKI and try to get it where each one had a sufficient impedance such that when you look at the grid, they didn't look like their impedance was too low. And we've published not too many papers, 2 or 3 papers related to this, the impedance part of tuning this. There's been others that have looked at this too, but I still think there's quite a bit of work that has to go on in that area.
Because how many converters do you have?
Oh, we have 30. Okay. That are all interconnected in this, yes.
Okay, and one last question. I like very much the idea to emulate the impedance between transmission lines. You represent there only, I guess, inductance impedances.
Yes, it's mostly inductive impedance. I'm thinking we have not really represented the resistance other than through a fault. When we do fault, we can do some that have a resistive fault, a high impedance fault instead of zero.
And the question also, is it prepared to emulate capacitance impedance? Because sometimes subterranean cables and so on, they have very...
Right, certainly like at black start, when you don't have enough load, a cable can appear more capacitive than inductive. We have our system, we're able to start it up at black start, but I don't know that we have intentionally tried to represent capacity. That's a good question. Yeah.
Okay, so thank you very much.
Thank you very much for your presentation. In the industry, more and more emulation and simulation are required before to install a new solar plant or wind or whatever. So my question is, have you tested any control of any supplier of real inverter, or your controller by your own only?
So all of the controllers we've used in our emulator were developed by us, but we certainly could take a third-party vendor and tie that into this. I'm thinking because we have had a couple of measurement vendors basically doing voltage measurements, phasor measurement unit that we have tied in and tested on our system. We have not done third-party inverters yet, but we could, yes.
Okay, thank you.
Okay, is there any other question in the, yeah, Neko? Okay.
Okay, can you hear me?
Yes.
Yes.
Okay, so Eneko Unamuno is asking, can you comment on the bandwidth of the power system emulator? Up to which dynamics can you emulate in your setup?
So our switching frequency of our converter was initially 10 kilohertz. And then I think in some instances we've run it also at 5 kilohertz. So that gives you an idea that at least we can look at phenomenon that are up to, I would say 500 hertz to 1,000 hertz. And that is also a little bit of a limitation of our inverters, IGBT-based inverters that we have right now. That was also a hope that with silicon carbide and maybe a second generation, we could push that out. But right now, at least power system events, we can look at up to about 1,000 hertz. Yeah.
Okay, perfect.
Which represents fairly well most power system events.
Okay, thank you.
Okay, thank you, Professor Tolbert.
Thank you.
So we are now moving to the second speaker. The following talk this morning is given by Professor Subhasis Bhattacharya from North Carolina State University. Professor Bhattacharya will talk about the solid-state transformer journey and the BitFET, a SiC-based bidirectional switch. Professor Subhasis Bhattacharya is currently Duke Energy Distinguished Professor at North Carolina State University. He received Bachelor Engineering from IIT Rourke, India, Master Engineering from IISc from India, as well, and PhD from University of Wisconsin, all in electrical engineering. He was with FACTS and Power Quality Division at Westinghouse RD and Siemens Power Transmission and Distribution from 1998 to 2005. He joined North Carolina State University in 2005, where he's a founding faculty member of National Science Foundation Future Renewable Electric Energy Delivery and Management Center, FREEDM, Advanced Transportation Energy Center, and Department of Energy Institute Power America. A part of his PhD research on active power filter was commercialized by York Corporation. His research interests are solid-state transformers with SiC devices, integration of renewable energy sources, microgrids, high-frequency magnetics, active filters, and the application of new power semiconductor devices such as SiC and GaN for power converters. His research is funded by several industries, such as National Science Foundation, Department of Energy, Advanced Research Project Agency Energy, Navy, or NASA. He has over 700 publications, 12 patents, H-index of 68, and almost 22,000 citations. Please, Professor Bhattacharya, the floor is yours. Microphone working?
Hello? Yeah. Okay. Okay. Yeah. Okay. Okay, good morning, everybody. I really want to thank the Mondragon University and for arranging this and for inviting us. Really thank you. And I've really enjoyed my stay this week out here and to see all the interested students and also the quality of the work as well as the PhD student defense. So I'm very honored to present to you today about our journey of the solid state transformer. And you will see why I call it a journey. And we have come a long way from the concept to a pilot demonstration in a decade. And I'm also very excited to present a very novel switch in silicon carbide, which is a bidirectional switch, and a converter application with this bidirectional switch. So I'm going to show you my last slide first, right? Because I want to actually get you interested. So we started doing work on solid state transformers in 2008. And in 2021, we actually delivered a complete solid state transformer to the Navy. So this is installed at a naval base. So this is a real system, a pilot demonstration. The Navy actually calls it a MUSE equipment, which is a mobile utility support equipment. So why does the Navy want a solid state transformer? Because once they actually make a ship, the total weight of things that can be carried on that ship is constant. So if they can actually reduce the weight of anything, then they can carry more ammunition. So the Navy always has to carry transformers because not only for the internal power system of the ship, but also whenever they go and dock at a port, anywhere in the world, they always use their own transformers to connect to the shore. So any weight reduction is going to be helpful. So that is the reason why the Navy is interested in a solid state transformer. So this project was funded by the Navy, and this is a solid state transformer, which is 100 kVA, and connection voltage is 4160, 4.16 kV, and 480 volts, all three phase. The Navy wanted us to use the 10 kV silicon carbide MOSFETs. So this is a very simple topology. You can see the medium voltage grid with a simple active front end, a simple two-level topology where we are using the 10 kV MOSFETs to block 7.2 kV of the DC bus. And then we have a DC to DC converter, isolated, a dual active bridge, and then a regular inverter on the output side generating 480 volts, right? Because we are using silicon carbide devices, 10 kV MOSFETs on the input side and 1200 volts on the output side, we can actually switch at incredible frequencies. So we are switching with 7.2 kV DC bus, these MOSFETs at 10 kilohertz hard switching. We are switching them at soft switching at 20 kilohertz at these medium voltages. And of course, the low voltage is switching at 20 kilohertz. Here is a snapshot of a waveform where we are showing these frequencies and the input and the AFIC voltages only. So as I said, this is a system that was actually delivered to the Navy. The Navy guys actually gave us this container, and you see this is the solid state transformer in blocks, and I'll talk about this a little bit, which is inside the container. And the size of the container is this. The Navy actually came to witness test this. So for that, we rented a generator. This is in the parking lot and tested this thing. The efficiency is around 96.8%. There was not really too much attention that we paid for power density. And therefore, this kind of shows a pie chart of what is taking space in the container itself. So I want to take you back to 2007 and 2008. So when we were actually writing the proposal for Freedom System Center concept, we at that time, from the renewable energy point of view, the solar, wind, everything was there. And we asked the question that why is the penetration of renewable energy resources not happening on the grid? And we said that, look, if I have to install a solar on my roof, then it is a project. And the cost of the project actually is more than the cost of the solar components. And so we said that we wanted to actually have a hub, which we call solid state transformer, which would be an integrator of all kinds of renewables seamlessly, plug and play, and that would be connected to the grid. So if somebody gave us this hub, then I have reduced the systems engineering and the project cost. And that would actually enable the increased penetration of renewables. So that was our thinking. The solid state transformer in that case, it not only is a bidirectional power flow processor, but it is also becomes an intelligent energy management system where you can actually do also the energy management and also all kinds of economics and trading. So then we said that this could be for residential, this could be for commercial, and this could be also tied to the legacy grid, and you can actually build upon the research from there. So that was the concept that we actually had when we were writing this proposal, right? Then as we progressed, one of the things that became very clear was the economics of the DC grid, both at medium voltage as well as at low voltage. And therefore we said that particularly in large metropolis or in university campuses, this could become a blueprint where you have a ring bus and you have all kinds of interconnections coming into the ring bus. So for large metropolis, this becomes a big important thing because you have several feeds coming into the city. Otherwise, people get stuck in elevators, and that's when we realize that, hey, something has to be done about redundancy, right? But a lot of people ask me that, solid state transformers have not replaced our distribution transformers. So why do you do research on it? And the simple answer is that actually the solid state transformer provides you the ingredients for all power electronic components and different areas. So if you look at a DC grid, you need the same functional blocks of a solid state transformer where you need a medium voltage AFEC or active front end, and you need isolated converters, either going from medium voltage to low voltage or even from low voltage to low voltage, right? So again, going back to this project a little bit more. So as I showed you, this was a very simple topology for the Navy SST. we use the 10 kV MOSFETs on the high voltage side, 1200 volt MOSFETs on the low voltage side. We developed everything starting from the gate drivers that are needed for the high voltage side. And that is the most important challenge of this entire project, is to actually do reliable gate drivers with a very high isolation voltage and a very low coupling capacitance for the power supply. The gate drivers for the low voltage side. And then to prove our point for pilot demonstration, we actually did all the controls in a compact trio, the National Instruments. So instead of having our own DSP and FPGA hardwares that we typically use in the lab. So this was basically to prove that, look, these systems can be made ready to go out in the field. There's a video link of this, this whole solid-state transformer is right now installed at the Naval Postgraduate School in Monterey, California, and it is actually powering their railgun facility. And then it is supposed to go to Port Hueneme, which is a naval base. This is also a naval base. So here are the specs of the transformer that are given out here. So I'm going to take you a little bit step by step of how this project was done, what are the important things. And the first important thing is the device, right? So for the 10 kV MOSFETs, there are two different packages that we used. We worked very closely with Cree and Wolfspeed for all of this work. And any of these packages, we are basically talking about a half bridge where one switch can take 6 die positions. So these 10 kV MOSFET dies are typically 300 milliohms, the new ones, and they are typically carrying 10 to 15 amps of current, each of them, depending on the switching frequency and the thermals that you provide. So you can argue that this half bridge module is rated at around 90 amps and 10 kV. So again, I want you to think that these devices don't come with a data sheet. There is no data sheet for these devices because they're being developed individually for particular projects, right? So we have to generate our own data sheet, right? So here is a little bit of a glimpse of this data sheet where we take these devices, where we have 6 of these in parallel, and we measure the RDS on as a function of temperature, going all the way from 65 milliohms to 180 milliohms, right, at temperature. We do the IV characteristics of these devices too. And then from the power electronics point of view, what is more important is the switching losses. So we do a very detailed characterization of the switching losses, both turn on and turn off. So I'm talking about EON and EOFs as a function of current and a function of temperature. So we do this thing at 2 different voltages, the 3500 volt DC and the full voltage of 7200 volt DC, right? And as a function of temperature. So this is a very important point because this is what is going to dictate all your thermals, and it is going to actually guide you through the design process of how you're going to actually select your frequency and the thermal requirements, right? Again, showing you block diagrams of blocks of how this is built, right? So this is the circuit. And one of the important things that we did, and you can see it here, is that because we had to actually make this into a container, this is inside the lab where we have it modular, where each of these blocks that you see are the 4 blocks of the 3 phases that are there. So 2 on the low voltage side, which are shown out here, and 2 on the high voltage side, which are shown out here. The backbone of the system is the cooling system, right? So we have a thermosiphon, which is a pipe-based heat sink. This is a cold plate with an evaporator, right? And so we can actually design this thing in such a way to dissipate anywhere between 1 kilowatt to 10 kilowatts of power dissipation or losses. So what I'm trying to tell you is that in this same footprint, I can actually increase the power rating of this converter from 100 kVA to almost 500 kVA without changing the footprint at all, right? So the gate drivers are hanging here, and then there are some sensor boards out here, the inductors, and then you see these transformers. So these are the high frequency transformers where we have the transformer and the inductors in the same tank. These are 20 kilohertz, and now you can see the size of these high frequency transformers at 20 kilohertz, and each of them rated at 40 kVA, going from medium voltage of 7.2 kV to all the way to 800 volt DC bus, right? This is now transporting the same things into the container. And again, I showed you the container. This is basically the Navy person during the witness testing of this thing, of this entire demonstration, right? And then, of course, my students went to the naval base and actually commissioned this, which is now, as I said, powering their railgun facility, right? So I'm showing you a project that we did over 2 years, almost 3 years. And I'm showing you just in a few slides, right? So here is the waveforms at 3.5 kV DC, 600 volt on the low voltage side, and around 28 kilowatt. So low voltage side converter waveforms, medium voltage side converter waveforms, switching at 10 kilohertz. This is the DC to DC, the dual active bridge, switching at 20 kilohertz, and again the low voltage side waveforms showing you. So as we go to higher voltage, the 7200 volt, which is our rated voltage, 30 kilowatt, medium voltage side converter working at 10 kilohertz and 25 amps, raising the currents to 30 amps. And again, the dual active bridge at different operating points or different control of phi. So what I want to prove to you is one very important point, is that we talk about silicon carbide, and what I'm trying to show you is that we are at a point where silicon carbide, high voltage devices are at a maturity point where these can be used for pilot demonstrations, and we have kind of retired the risks such that industry can actually now look at it for commercial applications and at least evaluate these for real systems. Okay. So now I want to go back, take you back to a little bit of the journey of these high voltage devices and what they can actually do in silicon carbide, right? So I'm going to be talking exclusively about 15 kV IGBTs and MOSFETs and 10 kV MOSFETs, right? So when we first started in 2008 with the Freedom Center, and we wanted to actually demonstrate a solid state transformer, I wanted to provide a baseline of what can silicon IGBTs do. So as you know, the highest voltage silicon IGBTs are limited to 6.5 kV, and for very good reasons, because of the thickness of the epi that's required and also the VF drop that's going to happen at 6.5 kV for silicon, right? So at that time, we wanted to build a solid state transformer, which was single phase of the 12.47 kV, which is the distribution voltage in the US, which is 7.2 kV. And we wanted a 20 kVA transformer because we were talking about replacing the distribution transformer that serves a few homes in the US, and output voltage of 240 volt split 120 volt AC. To do a simple thing like this, to block 7.2 kV with 6.5 kV IGBTs, you need 3 cascaded structures. And this is basically showing what the baseline or what is the limitation of silicon IGBT is. So we built the system where we have a cascaded H bridge with a dual active bridge, where we are only switching the 6.5 kV IGBTs at 1 kilohertz, and the soft switching, the dual active bridge at 3 kilohertz, right? So this entire system was built. We actually got dies from ABB for the 6.5 kV IGBTs. The smallest die that you can get is 25 amps, and then we get them custom packaged by PowerX. And so this was the first transformer that we built, that's why it is not optimized and bigger, and then the second and third one for these 3 cascaded structures. This is showing the waveforms or the test results for the transformer, again, with no cooling, and you can see what the core losses are. Efficiency is not that great because this is all met glass, and we are switching at 3 kilohertz for this. Insulation of the wire and other things, right? So there were 3 of them, as I said, built all 3 of them with normal convection cooling, and the test results for each of them at around 7 kVA. And these are showing a little bit of the difference of what happens when you have these 3 transformers, right? So then we asked the question that if we had silicon carbide devices, what would be the right voltage that we would need and what those devices can do? So if we have a 15 kV silicon carbide MOSFET, then we can actually block with a single stage 7.2 kV AC, which is going to be around 11.2 kV DC, right? So you have a margin to block this. So we actually have these 15 kV silicon carbide MOSFETs that were developed by Cree, right? And because we did not have enough of these devices, we actually did a H bridge on the front end, but only a half bridge for the DAB on the high voltage side. And low voltage side is pretty standard with these devices, right? Same rating and same structure. So now I want to show you that what is this 15 kV MOSFET, right? And why we should probably pursue it or we should not, right? So if you take these devices, right, and we as power electronics engineers are interested in the switching performance of them. So if you take them at 12 kV, and these are 10 amp dies, and if I fixed my turn on dV by dt to be around 45 kV per microseconds, because I'm trying to compare that later, as you see with IGBTs at 15 kV, then I see that the turn on losses can be anywhere between 37 millijoules to 77 millijoules, turn on losses. And again, why I'm talking about setup 1 and 2 is because in setup 1, I basically have a diode on the top side, and so the capacitive dump of the diode is not that much. In the second setup, I basically have a pole, and therefore I have the 15 kV MOSFET also on the top side, and therefore the capacitance of the 15 kV MOSFET is contributing to a huge turn on spike, and that is going to give you this much of losses, right? So now keep that in mind that you have something like 77 millijoules of turn on losses, right? When you come to turn off at around 32 kV per microseconds, dV by dt, you are talking about turn off losses are very small and 9 to 7 millijoules, right? Of course, we know that MOSFET being a unipolar device, that is the advantage of this particular device because the turn off losses are very, very small. It's a great device for turn off, but turn on is a big problem, right? So we said, yeah, we want a 15 kV MOSFET because as you saw, this topology got reduced to one stage. And if we have the 10 kV MOSFET, then we can definitely go to also one stage where we could actually now go to a 3-level front end and 3-level for the DAB and still solve the problem with one particular stage, right? So then we said, okay, that is great. What about the magnetics and what about the transformer, right? So this has been my passion for a long time since I was a PhD student on working on magnetics because I really believe that magnetics is the key thing for all power converter applications. And so here you see a coaxial winding transformer where now I want to point out, look at the size of this coaxial winding transformer. This is actually rated for 30 kilowatt, 20 kilohertz, and it is going from 12 kV to 400 volts, right? So 30:1 ratio. And look at the size of this. This is all toroidal cores, which are nanocrystalline. And this is the full operation of this transformer at 20 kilohertz and 30 kilowatt without any cooling. There is not even air blowing on top of it, right? So what I mean is that, you know, that these things are possible now, and these things can be done very reliably. Of course, there's a lot of research that goes into how you actually do this windings. Okay, so now there is something interesting, is that why should we look into IGBTs for silicon carbide? Of course, if you think about why people looked into IGBTs for silicon, right? Before silicon IGBTs were there, silicon MOSFETs were already there, right? And then, of course, the silicon BJT was there, right? So people went into IGBTs because of two things, right? One is that it had a MOS gate, so therefore you could gate it with a voltage, unlike a BJT, which is a current requirement for the gate. And the second important thing was that the current density of the die was much higher because of the bipolar nature of the device itself and the conductivity modulation that you get. So now if you fast forward that thinking to silicon carbide, right? So in silicon carbide, because of many device related reasons, which I'm not going into here, it does not make sense to actually build IGBTs below 12 kV because the forward drop will be very high. It does make sense to actually build devices higher than 12 kV, like 15 kV, and Cree has built IGBTs up to 24 to 27 kV blocking, right? Now, the question that you are going to ask is that, what is wrong with the MOSFET in silicon carbide, right? I already showed you 10 kV MOSFETs. I already showed you that we can take them and build the whole system, right? So why can't we just scale the MOSFET up from 10 kV to 15 kV? Yes, you can scale the MOSFET up, but the problem is the following, right? The 10 kV MOSFET, the epi layer is already 110 micron thick. To scale it up to 15 kV, you will need an epi which is at least 150 to 160 micron thick. And the MOSFET, the 10 kV MOSFET, which I said a single die was 300 milliohms, now would be at least 600 milliohms. So at room temperature, and MOSFET being a unipolar device, as you heat it up, it will go to around 1700 milliohms. And I will show you those, those are the numbers for the MOSFETs that we have. So therefore, it does become impractical for actually scaling up the MOSFET to 15 kV, and you definitely want to go into a bipolar structure where your VF drop is not a function of temperature, but of course there is no free lunch because IGBT has a big problem with the EOF drop. So as a function of temperature. So we did a project which was one of the biggest projects that RPE funded, and this was over 4 or 5 years, where somebody was producing these IGBTs for the first time. So Cree actually was making these IGBTs, 15 kV IGBTs for the first time. And my job was to take these IGBTs and get them packaged and to actually make a complete solid state transformer. So you can imagine, right? Somebody is making these devices for the first time where two devices don't look alike. So anyway, so for that, we actually went into a 3-level poll because we wanted to go to 13.8 kV with these 15 kV IGBTs. And for the AFEC and for the DAB, again, a 3-phase DAB where we have 2 secondary windings because I had to do this to meet the efficiency requirement with the 1200 volt MOSFETs on the low voltage side. So because this is IGBT, we are switching the front end at 5 kilohertz and we are switching the dual active bridge soft switching at 10 kilohertz. So this entire system was built. I'm just showing you a couple of slides, where we have an auto transformer outside that actually controls this transformer, which actually steps it up to medium voltage. And then we have these 3 racks where we have the 3 poles of the AFEC or the active front end with the inductors. And then we have the dual active bridge, 3 poles, high voltage poles and the low voltage poles, and the transformers are on the bottom. So this is the transformer. Now you can look at the size of this transformer, right? This is a 70 kVA transformer going all the way from 22 kV to 800 volts and at 10 kilohertz, right? So these are the waveforms where we grid tied at 4160 and 8 kV DC bus, the grid currents, the voltages on the pole, and the grid side line voltage and line current, right? Coming to the DC to DC part of this converter, right, where we have a 3 level on the input side. So remember the topology is the following, is that we have 3 single phase transformers to emulate a 3-phase transformer, because we do not want to meet the BIL requirements of a 3-phase transformer. So, but each of the transformer has 2 secondaries, right? So what I'm showing you out here is one of the primary voltage, which is a 3 level, and the primary current, and one of the secondaries. Now, again, you are going to say that, hey, these currents look really bad because they are not sinusoidal. Yes, they are not sinusoidal, and they are not supposed to be sinusoidal because of the parasitic capacitances and the parasitics of the transformer itself. So the transformer, actually, now you have to understand the magnetics very well and the coupling capacitances and the parasitics of the transformer, as I'm showing you out here. So most important thing to pay attention to is the primary to secondary coupling, which is, in this particular case, was around 1200 picofarads. So now you can see the size of the transformer at 10 kilohertz and 70 kVA. And this is immersed in oil. The dielectric of the oil is 3, which basically means that if you did not have oil and had air, the transformer would be almost 3 times bigger, right? So these are the results where at different voltages, the 4160, as I showed you, on the grid tied, a little bit lower voltages, and with the 7 kV DC bus, and the grid side voltage and the currents, and also showing all the filter voltages with the parasitics of the capacitance of the inductor and the high dV by dt that is being coming from the converter side. I talked about the transformer. I'm going to quickly go through these things. So one of the important things, and the reason I want to talk about the transformers to the students particularly, is that now you want to really pay attention to the high frequency transformer and characterize it. So here's the characteristics of the transformer impedance plots. And you really want to pay attention to the resonance points of the transformer, right? So based on this, we can then actually make a very detailed model of the transformer as we are showing out here, right? And it is very important to understand this model because of the resonance point and the parasitic capacitances and evaluate what that means for your control. So the control has to be aware of these resonant points and try to avoid these resonant points. Yeah. This is the other transformer that I showed you for the Navy project. And here are the details of this thing. One of the important things that you will realize is that we actually want, this is all nanocrystalline cores, right? So one of the important things that you'll realize is that we want a magnetizing inductance, which is very, very high. And so, for example, in this case, the total leakage of this transformer was around 1.8 milli on referred to the primary side, and the magnetizing is actually more than 300 milli. So the ratio of the magnetizing to the leakage is very high. And that is an indication of how good the transformer is in terms of efficiency and losses. We did another very interesting things for the students here for the transformer, because we actually have a Faraday shield in the transformer. And that is to create an equipotential that you can now tie to, now you can tie to something, some voltage or equipotential, such that you can manage the parasitic capacitance of the core, between the core windings and winding to winding kind of thing, right? So these are the different tricks and different things that you have to do actually for these kind of high frequency transformers. Again, you can see the size of this thing. This is a 40 kVA transformer, you know, at these voltages. Again, characteristics of this transformer, just like what I showed you earlier, and the understanding of this such that you can actually make a very good model and for your controls. So this is what we are aiming for here. So this transformer compared to the other one was actually a little bit worse because we wanted a parasitic capacitance or a coupling capacitance of 1000 picofarads, but we landed up with almost more than 2000 picofarads of this of the parasitic capacitance. Okay, now very quickly, I want to show the students and everybody that what do these devices look like, right? And so I'm now showing you that this is the die for a 15 kV silicon carbide IGBT. The die is very small. This is a 20 amp die, and it is only 8.4 millimeters by 8.4 millimeters. There are two diodes, JBS diodes, connected in series because each of them is blocking around 8 to 10 kV. We had enough space in this package to actually put two dies in parallel, and that is what we did for IGBTs as well as for the 15 kV MOSFETs. So if you go to some of our papers, you will realize that we have done a very fair comparison of the 15 kV IGBT with the 15 kV MOSFET because we had exactly the same package and exactly the same thermals. So we could do that. So this is IGBT. I'm just showing you that this is the reason why the world uses IGBTs, right? Because the active area or the die size is very small. So the current density of the IGBT or a bipolar device is always going to be much higher than a unipolar device. Okay, so we also have the package of the MOSFETs in the same package or a co-pack. Now we have gone into the structure where we actually have standardized this kind of a package with PowerX, and we package all these devices, you know, 3.3 kV, 6.5 kV, as well as even the 10 kV in this particular package. We have used this package and this package, as I've shown you earlier. We have done some work with the 3.3 kV, which I will show you with this particular package of GeneSiC, right? So again, moving forward. So as I said, you know, this is a very important thing. Again, I want, you know, to emphasize on is that I always believe that, you know, the device, I think power electronics engineers should understand the device and not take the device as a black box, right? And so you see, this is the important point, is that the IGBT, the VF drop is not a strong function of temperature, right? So if you take the 15 kV IGBT at 10 amps, you're going from 4.8 volts to 5.2 volts with 25 to 150 degrees C. But that is not the case with the MOSFET, right? The 10 kV MOSFET, the earlier versions, which were 450 milliohms, you know, went from 450 milliohms to 900 milliohms as a function of temperature. If you take the 15 kV MOSFET, you can now see what I meant by 600 milliohms to almost 1700 milliohms. And therefore, this is not a good device to use. And that is the reason why you should go into the IGBT. But again, you know, we need to do a fair comparison because, as I said, the IGBT EOF losses are a strong function of temperature. So here we are doing the fair comparison of the IGBT versus MOSFET, and you will see that the IGBT will actually have, of course, more switching losses, but the IGBT is going to start winning when you have more and more current, right? And the higher power and lower switching frequencies, right? Compared to the MOSFET. Okay. So one quick thing is that we had a big problem when we first started using these devices because the dV by dTs of these IGBTs, where you can see now here that the turn on dV by dt was 110 kV per microseconds, and these are punch through devices, so punching through at 5.65 kV, and so therefore there are two slopes, right? So these kind of numbers power electronics engineers have never seen, and even with silicon, you know, if we get 10 kV per microsecond, we get concerned. So the fact that our gate driver was actually working at that point was itself remarkable to us at that time, right? So this is all at 11 kV switching, right? Okay, so one of the first things that we have done, and over the years, we have actually done many versions of it, is that we have done lots of different versions of the gate driver, particularly, as I said, focusing on the coupling capacitance of the isolated power supply, right? And we have come to a point where we have around 1.43 picofarads measured at 110 megahertz, as you see out here, and with isolation of 18 to 20 kV. And we have done a little bit better than that. We have gone to almost 0.6 picofarads, but the structure looks a little more complicated. But the other important thing that we have done is we have actually done an active gate driver, where we have a CPLD sitting on the gate driver itself. And again, this CPLD had to be very hardened CPLD, because obviously this is a very high dV by dt and noise environment. So with the CPLD, we can actually now make an active gate driver where we can control the Miller plateau. So by changing actively the resistance of the gate, we can now control the switching dynamically and the Miller plateau of the MOSFET. The other important thing that we do is that, of course, we have a DSAT on the gate driver. And again, as I'm showing you, this is a very important step that we always do, is that we do the short circuit and avalanche characterization of these devices. So we take a die, the 10 kV die, and we put 6,000 volts on it, and we intentionally cause a short, right? And the die, which is supposed to carry 10 to 15 amps, now goes all the way up to 220 amps, and we confidently turn it off with our gate, and we can do this in 2.4 microseconds. So we can detect, turn it off in 2.4 microseconds, right? Nothing happens to the die. And so what I'm trying to convey here is that these are the steps that we had to do. We had to do to make the system work. And these are the steps that that are very possible to do, as you see out here with this gate driver. With the active gate driver, we actually also have another interface board where we have a FPGA, and we can now get signals, optical signals from 12 of these gate drivers, and now we can start doing diagnostics and prognostics in the FPGA of this structure. So why 12 of them? Because I was looking at a 3-level NPC structure, right? Okay. Now, sitting on the gate, I can actually measure the VDS, or the voltage across the device. And that is the starting point of my diagnostics, right? Because if I actually sense something is going wrong with my VDS, then I know that my RDS on is actually changing. So this is a boost buck converter continuously operating, and we are sitting at the gate driver and measuring the VDS. We can also measure the temperature and compare it with our thermal camera, right? Okay, next, very quickly, right? So again, coming back to the SST. So now we actually ask the question that, you know, if you are a microgrid operator and you have a microgrid and you go to the utility and you say, hey, I want to connect my microgrid to your grid, So the utility is going to ask you two questions. One is, of course, the galvanic isolation between the microgrid and the utility. And the second thing is that the utility is always going to ask you is that how do you make sure that you are in sync with me? And because you cannot answer that question, therefore, the utility is going to say that, hey, we need to actually control the total import and export of power, which basically means a back-to-back converter. So we actually then asked the question that, and there was a company in the US which was actually selling these back-to-back converters with silicon-based and with 60 Hz transformers on both sides to go up to 13.8 kV for microgrid to microgrid interconnection or microgrid to grid interconnection. So we asked the question, what can silicon carbide do, right? So we had this big project from Power America where we wanted to use the 10 kV MOSFETs, and we now have a 3-level pole structure as our building block, but we have two 10 kV MOSFETs connected in series per switch for this interconnection of the 13.8 to 13.8. Again, the same poles all over, right? So we have an AFEC, a dual active bridge, and again, repeating the same thing out here. We are now switching these things with the series connection at 10 kilohertz, 10 to 12 kilohertz, and we are switching the DC to DC part at 20 kilohertz, right? So this is a system that we have built. And again, before we built this, the first thing we had to do was the series connection, right? So what I'm showing you here, and again, you can find a lot of our papers talking about the series connection and the details. I'm just showing you here that the turn-off waveform of the 10 kV MOSFET at a 12 kV DC bus, so 6 kVs across each of them, dynamically getting balanced with the 12 kV DC bus. So we built this as our building block. This is again the heat pipe based heatsink for this particular case, and this is showing you results at 12.5 kilohertz at a low voltage and around 10 kilowatt. Yeah. So we have taken this structure and we built the entire system. And what I'm showing you here is just the operation of an AFEC or an inverter, where we have three of these guys, three of these poles. And this is how one pole looks like, you know, with the DC bus and the devices sitting on this heatsink. And again, this is 25 kilowatt operation at a 5.5 kV of DC link, right? So again, you see, the point I'm trying to prove to you is that we can actually use these devices in continuous operation, as I'm showing you here. This is not a 2-minute result or 2-second result on the scope. This is, we run this thing continuously to get thermal evaluations. And we can run these things and confidently at these voltages, and therefore we can actually build these kind of systems. This is the DC to DC part of it with the same poles and 3-level and 3-phase. And again, this is done at a lower voltage. But this is the ongoing work that we are doing now, right? Okay. So I'm going to skip this. We connected 3 of these 3.3 kV devices connected in series to build a pole and actually emulate a 10 kV device and turn on, turn offs of these things for a complete converter, right? Okay, so I'm going to actually switch in 5 minutes to talk about the bidirectional switch, right? And again, I'm very lucky because we have Professor Baliga as a faculty, who's my colleague here. And of course, he's the device person. As you know, he's the inventor of the IGBT. And Doug Hopkins, who was a packaging person. And we actually have this big project where we actually build the device and then make a complete converter. So of course, the advantage of a bidirectional switch is known to us as power electronics engineers. And I'm just quickly showing you that this is the monolithic device, which is like a common drain MOSFET, but a monolithic device with 2 gates and operating in the first and third quadrant, right? So we designed the device, we built the device, and the device is built in XFAB at a commercial large foundry. We package the device into a single 4-terminal device like this, and then we actually use them for a solar inverter like this, where we have a grid tie with the solar. So again, I'm showing you the last slide first, where we actually built this converter system with this particular topology. So basically, we have a PV, a DC on this side. We have a chopper, high frequency isolation with high frequency transformer. And then we go directly from high frequency AC to the grid frequency AC. There is no DC storage out here, right? And so you see the prototype here. These are the waveforms across the transformer. One of them is the chopper waveform from the DC side. The other one is the high frequency AC. This is the current on the transformer side, and again, the current on the grid side. So this is pretty interesting, right? Because you now have a device, which is a bidirectional switch. And again, I want to prove to you, without going through all the device stuff here, in the interest of time. So by the way, I wanted to mention to you that this device is basically a 50 milliohm device at 1200 volts, right? And each of these dies is rated for 20 amps. We have a second generation where we have cut down the RDS(on) to half, around 26 milliohms, and I'll show this. So what I mean by the bidirectional switch is that if I do the IV of this switch, then I basically have a symmetric first and third quadrant operation. This is just the blocking of the device. We have detailed measurements of these capacitance of these devices, which I'm not going to go into, and I'm going to skip these slides here again, showing we have paralleled these devices in a module, and again showing the parallel characteristics, parallel device characteristics at this point, right? So I just want to quickly show the Gen 2. Yeah, so a little bit device design change, and that actually reduced our RDS(on) from 50 milliohms to 30. Actually, we're measuring around 26 right now. And this also has a little bit of the die where we have a temperature sense resistor. So every die, we will have a temperature sense from every die, right? So you can now start thinking about the diagnostics and the prognostics from this. So as I said, 27 milliohms of this thing, and these are the turn on, turn offs. So now I want you to focus on this a little bit for 1 minute, right? We have a device which is 800 volts, and we are testing this thing at 800 volts, 20 amps. The E-on is around 1.1 millijoules, and the E-off is 0.25. So you're talking about a total loss of 1.3 or 1.4 millijoules, right? So just keep that in mind. So now you can now see that you have a RDS(on) which is like 27 milliohms. So let's say 30 milliohms, right? You have a E-on, E-off total of 1.4 milliohms. So now you can start calculating the losses if you're switching at 50 kilohertz or even at 100 kilohertz, right? So here is a quick summary of things that we compared the Gen 1 and the Gen 2 devices in terms of the capacitances and things like that. Very detailed comparison with our Gen 1, Gen 2s, right? And then showing the different E-on, E-off tests and the converter tests. So what I'm going to leave you with is, again, a little bit detail about our converter system. We are switching at 50 kilohertz for this with the bidirectional switch. And this is grid tied at 240 volts RMS single phase. And here's the results, which I already showed you. Here are the measurements from the Hioki power analyzer. And again, the distribution of the losses. So this whole prototype was not optimized, particularly from the magnetics point of view. So if you just concentrate on the semiconductor losses, right? So we are talking about around a little bit more than 95%. On the semiconductor efficiency, the total one, we are talking about a little bit more than 95% because the losses in the magnetics are not optimized. But if you just look at the semiconductor efficiency at a power rating of this much, we are talking about almost more than 98% and to 97% at the low 20% rating. So with that, I think I just want to stop here because of the interest of time. Of course, there's a lot of interesting things to talk about, but I wanted to give a kind of a synopsis that what can high voltage silicon carbide devices do and why we should look into that, what systems can be built, and also this very exciting new device, which is going to be, so I always think that power electronics takes a quantum leap every time there is a new device. And so we are at a cusp here where we have a new device, which has been the holy grail of power electronics. And now this can enable a lot of different things. Thank you very much.
Working? Yeah, okay. Okay, thank you, Professor. There are a couple of questions. If they are short and fast, I'll go there.
Thank you for your presentation. It was really impressive. It's not typical to see works with silicon carbide with 10 kilovolt. So thank you very much. I have a question related to this topology for a transformer, the solid state transformer, in comparison with a regular typical linear converter. Normally in the market, it's not easy to see this kind of topology because of the reliability. Normally because the quantity of the semiconductor. So I don't know now, in your opinion, with this kind of semiconductors, with 10 kilovolt semiconductor, or we are going to see less semiconductor in this topology, it will be more easy to introduce this topology in the market.
Yeah, so one of the main aims that I had since I started working on silicon carbide was actually to retire the risks of using high voltage devices such that industry now picks it up. So you see the major problem of, you are absolutely right that unless the reliability of the 10 kV MOSFETs and MOSFET based topologies are proven, industry is not going to actually adopt it, or industry is not going to commercially evaluate it. So my thinking has always been that I want to actually retire all the risks that are associated with these high voltage devices, such that I'm trying to tell the industry that, look, these things are actually ready for you to do an evaluation for your commercial applications. So that has been my thinking. But what you say is right. I mean, I think that's why I'm trying to take a different view of this, because, you know, as you know, the whole world is doing research on cascaded H bridges because of the low voltage devices, because you can use the low voltage devices. And that is what industry is going to adopt first also, and industry is adopting that. But my view is that, look, these devices are mature, they are reliable, particularly the 10 kV device. And therefore, I'm trying to tell industry that, look, the risks are retired. for you to actually evaluate these for serious commercial applications.
Okay, thank you.
Thank you, Professor. So we are taking the coffee break now. We are supposed to come back here at 11:30.
From Technical University of Denmark, who will talk about switch mode audio power amplifiers optimization when using GaN FETs. Michael Andersen received the master and PhD degrees in power electronics from the Technical University of Denmark, DTU. He's currently a professor in power electronics at DTU, where he has been deputy head of Department of Electrical Engineering from 2009 to 2022. He's the author and co-author of more than 300 publications. His research group is very innovative, with 76 field inventions and 9 startup companies. He has been thesis advisor for 47 PhD students and more than 200 master science students. His research interests include switch mode power amplifiers, power converters, power factor corrections, switch mode audio power amplifiers, and very high frequency power converters. He also acts as an expert for the European Research Council. Please, Professor Andersen, the floor is yours.
Thank you very much, Mika. Can you hear me? Perfect. And thank you very much, Juuso, for inviting me here for this seminar and for the very nice PhD defense yesterday as well. It's been a pleasure. I think it was Monty Python that a long time ago said, and now to something completely different. Very much different from the first two presentations by the two professors over there, because I'll be speaking about something where you can hear the stuff, audio amplifiers. And I think Mika, he introduced some of my merits, so we'll move on from that. But I've been in the power electronics business for more than 30 years from the university, doing a lot of collaboration projects. And one of those that has kind of run over the most years is actually this area of switch mode audio power amplifiers. But first, 2 slides about my university. My university is actually founded by Hans Christian Ørsted, who is the guy who discovered electromagnetism. And yeah, Denmark is let's see if I can find the pointer, a very small country up here. We do, although have Greenland and Faroe Island in our kingdom, so we get a little bigger. But the small country, we have 3 campuses. I'm in the main campus in Lyngby. We do also have some test facilities. You can see a couple of wind turbines here, which is one of the things in the energy industry where Denmark is famous. My research group covers power electronics and IC design. So making power electronics smaller, but also doing IC design, and over the years, Class D audio, which is my topic selected for today. But we've also worked on piezoelectric transformer-based switch mode power supplies, where you can actually make a switch mode power supply with no magnetic components. That could be used in medical scanners or other places with a high magnetic field. And recently we have started working on flexible and printed electronics that could be used for various applications. In the power electronic area, we have also been moving up in frequency to high frequency and very high frequency switch mode power supplies, because the passive components, they scale inversely with the frequency until you get penalized by the losses that typically increase by frequency. But it would be really nice if we could shrink the power supplies and then eventually close the loop and put it back into an IC, everything. And that's also part of what we are working on. And of course, as the previous presentations, challenges in efficiency, size, performance, and the components covers both the active and passive components, of course. And already here, we have scaled down in the power range. We cover from microwatts to multi-kilowatt range in our research. Class D power amplifiers, driving loudspeakers as the ones that make you listen to my speak here. The impact over the years is everything from mobile phones, tablets, PCs, TVs, sound boxes, Bluetooth speakers. It's everywhere now. I don't even think you can buy a Class B amplifier anymore. Everything is Class D, switch mode. That's great. We've made an impact. But it's also a challenging application because the dynamic range is in the range of 120 dB from silence to the sound of a jet or something like that. The distortion has to be extremely low because you want to listen to the music and not all the bad stuff. And the bandwidth of the reproduced signal, it's not only 50 hertz or 60 hertz, but it's more than 20 kilohertz. I can't hear 20 kilohertz anymore, but many of you can, I'm sure. The impact that we have made is actually a number of, it started out as startup companies. One within Bang & Olufsen, which is this famous Danish design of audio and video equipment. They were actually the one who originally had the problem that amplifiers they had to design around an extremely large heatsink. So that limited their fancy design because they need to have this little heatsink. If they could get rid of the heatsink, they could make more fancy design. So that was the task we got. Bang & Olufsen, well, I hope they won't hear me now, but they're maybe not famous for the very high precision, very low distortion music. But the distortion had to be low enough so you won't recognize it or hear it. But just low enough, that was good enough. You can get find other hi-fi manufacturers that really push the distortion down. But it was okay if we could make something that was good enough, as long as we could shrink the amplifier. Another startup company was something called Toccata. They were acquired by Texas Instruments after a couple of years and had a branch, and that's part of their Class D now. And then the third startup company is one called Meos Audio that made a free-level Class D amplifier, and they were acquired by Infineon and is now one of the Infineon branches in Denmark. The plot here is the total harmonic distortion versus output power, just an example. And I think the different colors are different frequencies of the input signal. And the Bang & Olufsen level was just get below 0.1% of TSD, then it was good enough. Examples or the principle of a Class D amplifier. it's a switching output stage that could be a single leg or an H-bridge, which you ran push-pull or even as a free level output. And then a comparator, it could be either a pulse width modulation or some kind of a phase shift self-oscillating modulator like this one, or hysteresis-based self-oscillating modulator. And then a feedback loop around it. So you suppress distortion and etc. in the frequency band of interest, which is the hearing frequencies. A couple of observations made on Class D amplifiers is that the power density is mainly limited by the output inductors. It's not the output transistors, and yeah, no heat sink at all here. We use the PCB for the heat, and then actually the efficiency or the temperature is limited by the MOSFETs on the output stage. And yeah, you could say we could choose MOSFETs with a low RDS(on), high capacitance that will give you a high efficiency at full power, but reduce efficiency at low power. Or you could choose, yeah, what somebody would call a worse FET transistor with a larger RDS(on), but a lower parasitic capacitances. And you will have lower efficiency at full power, but higher efficiency at low power. So which one to choose? Well, you need to look into the signal that you want to reproduce. And this plot shows the amplitude distribution versus signal amplitude. And the red one is a sine wave. And of course, the sine wave only have 1 in amplitude at the very point, one place, and -1 in the other place, and then almost flat in between because it transits from +1 to -1. If you look at the music, actually, audio, then the major part of the audio is actually around 0. Almost nothing at full power. So two very different signals, very much different. Actually, traditionally, amplifiers are being tested by a 1 kilohertz sinusoidal signal. Because that's traditional, the signal that we say, okay, music, that's sinusoidal. But the distribution of a music track is nowhere near a sinusoidal. The distribution here is linear, and if you turn it into logarithmic, it gets even more pronounced. And we actually examined a lot of different audio tracks, all the gray ones here. And then we averaged it out, and the average distribution of audio or music tracks is something that looks like the full line here, or full line curve here. And up here you have the sinusoidal. So very different signals that our amplifier actually has to reproduce, because it's going to reproduce music or speech, which is very much like music. So music and speech is the same in my presentation here. So how could we test? Because we cannot test an amplifier with all the music tracks. Will never be finished. So we came up with a, you could say, artificial signal that resembles audio. And that's the partly dotted line here. It has most of its content around 0, but still it has the peaks, like the very high volume bass or something like that, that really hits the high volume in a music track. So that we can actually test the amplifiers with a continuous signal, but still represents the audio, which is the one that is going to the working condition of the amplifier. We came up with this, and actually the US energy, what's it called, EPA's Energy Star program, they're actually considering this test signal to become a standard test signal for audio, testing audio amplifiers. That's great. Yeah, if you have a Class D or a switching state, then you can turn the amplitude at every instant into a corresponding duty cycle. At the duty cycle 50%, it would be, the average would be 0 on the output. And the full duty cycle, you would have full output, or 0 in the duty cycle, you will have minus full on the output. So the amplitude is directly mapped into the duty cycle. A little observation is that actually 90% of the audio, the music, is in between here. And I think that's something like 30, no, it's less than, I think it's something like 38% from here to here. So 19.19 in duty cycle in this difference here, something like that. Then we go back to the Class D amplifier. It has an output filter. Typically made like a second order filter. You have an output inductor. You have the loudspeaker that is considered as an ohmic load. And then you have a capacitor to short the high frequency. So it becomes a second order filter. And typically you design it with a Q value of 0.7 or something like that. So a very slow roll off around the cutoff frequency. And that's because the guys who design the control loop are power electronics guys. They're not control guys. So they usually only work with a pole and a 0 and can place them in order to make things stable. But if we want to reduce the size of the output filter, we would like to reduce the inductance, but that would give you a higher Q of the output filter. And that would be more troublesome to make it stable. But high Q can be handled if you make some kind of full state control, for instance, where you measure both the output voltage but also the inductor current. Then you have better control of the filter and can easier make it stable, or use more advanced control methods as well. The cutoff frequency, well, we can't do that much about that. It has to be higher than the audio band, which is 20 kilohertz here. But we can't just move it up, because the switching frequency will be there, and it needs to be dampened sufficiently so we don't emit too much of EMI. So there are limitations of how high we can push the cutoff frequency to compensate for the lower inductance there. But something can be done, and of course I've selected these quality factors because I'm going to use them in the next one. If we look at the inductor and look at the ripple current amplitude divided by the value of, or the, you could say, average of the current in the inductor in that switching period there. And then let's just take the Q of 0.7. It will look like this ratio here. When the amplitude of the ripple current is less than the average of the inductor current at that point, we will have hard switching. As soon as the ripple current is larger, it needs to be a little bit larger because to compensate for the energy in the capacitance, but that's not that big. As soon as it's larger, you will have soft switching. In the half bridge, we need also to make sure not to have short circuit, so we need to have a little dead time. And that dead time will cause distortion in the audio signal. Larger dead time, larger distortion. So a small distortion as possible, but if we can utilize, when we utilize the soft switching, we can actually avoid the distortion from the dead time. So zero voltage switching, almost equivalent to no distortion. So if we can be above the line here at 1, ratio of 1, it would be really great because then we don't have any distortion from the power stage itself. And you can see increasing the quality factor, at 8, we can actually have, you could say, no distortion, at least when we use a modulator that is self-oscillating. The dash one, FF, is fixed frequency. So that's a constant frequency. That's a pulse wide, constant frequency pulse wide modulation. The SO is soft switching, either phase shifted or hysteresis based. So you can also see that actually some of the soft switching can perform better. For instance, the quality factor of 4. But let's move on here. If we look at the losses in the FETs, the inductors, and the sum of the losses, I've plotted an example of the losses in the MOSFETs for different quality factors. That's the colors, and then the solid or dashed is the self-oscillating, respectively the fixed frequency. So you can see that in the inductors with a quality factor, low quality factor, we have almost no losses in the inductors, output inductors. So they are just big to create the inductance value. But then there's a lot of mass there, just sitting. But on the MOSFET side, both the quality factor, and that would be the ripple current, but also, of course, the amplitude of the current at the different duty cycles kicks in. And summing up the losses, you can actually see that, you can get some very low losses there in the quality factor of 2 to 4, some in that range in between, but then at higher output levels, it changes a lot. So could we combine this with some of the information about the music signal? Sorry. There it was. Yeah. So the plots here, this is the power loss in the MOSFETs. The left plot here is for sinus input, and the other one is this dynamic test signal, read music signal. So this is the, you could say, total losses in the MOSFET for music signal. The first two one is the quality factor of 0.7, then 2, 4, 8. And we have the distribution of losses in the gate losses, conduction, switching, and some reverse conduction as well. And yeah, FF is the fixed frequency, the other one is the self-oscillating. And same principle with the losses in the inductors, and then summing up the plots here in the right-hand side, we actually see that for the dynamic test signal, we have a minimum here in the range of 2 to 4 of the quality factor. So that could be really interesting. We did 2 different amplifiers, 150 watt maximum output power. Number 1 switched at 500 kilohertz, number 2 at 1 megahertz. But let's see, both have a quality factor of 4, and we assume the 8 ohm loudspeaker. And AMP1 used the GaN system MOSFETs, and AMP2 used the EPC MOSFETs. Both were H bridges or bridge-tied load. And we selected the self-oscillating modulator for it. And the PCBs here, and the scale here is in centimeter, and that's for a 150 amp loudspeaker. We tested distortion, and yeah, this is pretty good for a first prototype of each of those. And please remember the efficiency plot here is logarithmic scale. If it was linear scale, it would look like this. But it's easier to see the difference between the 2 amplifiers at very low power if you do a logarithmic scale, but it doesn't look as nice at first glance. Then we tested those 2 amplifiers, and now it's also two columns here. The first one is amplifier 1, and the next one is amplifier 2, and then the quality factor of 0.7, 2, 4, 8, basically the same principle. And now we can see that we have a minimum losses and the quality factor of 4 as expected, and it's actually very low losses in the FETs, and we actually selected this one. This one is using those GaN FETs, and as you'll probably tell us a little later, the dies are extremely small. Being so small, it's very difficult to get the power away, the power loss out of the out of the GAN FETs. So it's actually beneficial to select somewhere where the losses in the FETs are minimum. The inductors down here, they are large, very large, and also a lot of mass. So they can actually handle a couple of watts of power loss very easily. And actually you see that the inductors, the difference between a sinusoidal test signal and a dynamic test signal is insignificant. The MOSFETs, they do get hotter testing with a sinusoidal. So we tested and used a thermal camera and recorded the temperature. This test here is with a sine wave. We got a GAN FET temperature of 108 degrees Celsius, inductor temperature of 92. That was amplifier 1, and amplifier 2 down here, 122, 103 degrees Celsius. If you test with the music signal, you get a more even distribution of the temperature as well. So that's extremely nice. And yeah, the product can get colder and you can get it smaller. So, and this is this was the temperatures that we saw before. If we look at the boxed power density, so taking each of the amplifier and putting it in a box, you get these volumes here, and compared to a couple of prior art using silicon MOSFETs, you actually see that we can double the power density, which we think is pretty cool. So, introducing GAN FETs in a switch mode audio power amplifier. We take advantage of this test signal, which actually represents the actual working condition of the Class D amplifier for audio. We can select the GAN FETs for the application, low RDS on, but we still need to move the any switching losses away from the MOSFETs. And we can do that by actually selecting a high Q filter, so we have a high ripple current in the output inductor. And then we dissipate, or you could say we take the switching losses out of the MOSFET and dissipate it as some losses in the inductor. And they are larger and can easier handle the losses there. So they won't get that hot. So we're actually able to double the power density, even though we have doubled the switching frequency as well, from 500 kilohertz to a megahertz. And we can make everything have a better balance in temperature, so we don't have hot spots, and especially not around the GAN FETs. So yeah, this concludes my presentation. Thank you.
Thank you, Professor Andersen.
Yeah.
I don't know if there is any question in the audience. What about in the chat? No questions? Okay. Subhasis, okay.
Thank you. This was really interesting from my perspective, and also I think from my perspective and also for the students, because I think this is something really impactful what power electronics can do. I'm interested to find out from you a couple of things. One is that as you increase the Q factor, that has an impact on the device voltage rating for your GAN.
The device?
The voltage rating of the device.
Yes.
Right? So, so could you comment that as you did all this, did you see any dynamic RDS on or current collapse with the GAN devices? And also, I think in general, I mean, I see the philosophy of the temperature balance, but could you comment on that the interaction of the Q or the design issues of the Q with respect to the voltage rating for the GAN devices and which direction we should go?
Yes, of course, you cannot just increase the quality factor to 10, 100 times or anything like that, because as you correctly point out, it will require an overhead in the voltage on the switching devices. But a quality factor of 4 can be handled, because you would anytime not pick a GAN device that is just a few volts above the rail voltage of your power supply there. You would have some headroom anyhow, and that can be handled. And yeah, as mentioned, you need at least a more than power electronics designed control loop. You need a full state control for a high Q filter there to have a correct or have it stable at all points.
Another quick thing, can you please comment on the slew rates that you need to achieve in the switching of the GAN device?
Of course, we would like to switch as fast as possible, but we have long time ago, and it's the same with the silicon devices. We've seen that the slew rate does not create as much distortion as the dead time. The dead time is the major factor for the distortion in the circuit. So even differences in the slew rate, it doesn't have as much impact as the dead time has. But of course, we would like to switch as fast as possible, because switching slower, you would have some switching losses in the devices. And yeah, our experiences, yeah, get as low losses as possible in the GAN devices, because they are so small. And we've also seen GANs with different temperature, and most probably because of the difference in the hand soldering from device 1 to device 2 to device 3 and 4. So yeah.
Thank you. Thank you.
Yeah.
No more questions? Okay, so thank you very much.
Thank you.
Okay, yeah. So let's let's go to the next presentation, okay? It's a pleasure for me to give now the floor to my colleagues, Igor Baraya-Chaburu and Joshua Puru, who will talk about the past, present, and future trends in power electronics. Dr. Igor Baraya-Chaburu received the bachelor, master, and PhD degrees from Mondragon Unibertsitatea. He joined the electric energy department of Mondragon Unibertsitatea in 2009, where he currently works as a lecturer and researcher. His main research interests include power semiconductors and power converters. He has worked on the development of active gate drive filters for the series connection of IGBTs, drivers for silicon carbide MOSFETs, design of multi-level converter as well as high-density power converter, and has published several papers in these areas. He has supervised 5 PhD students, and he has also participated in different industrial projects related to these fields. I will introduce Joshua as well, okay, even if he's speaking later. Dr. Joshua Puru received the bachelor, master, and PhD degrees from Mondragon Unibertsitatea. He joined the electric energy department of the Mondragon Unibertsitatea in 2015, where he currently works as a lecturer and researcher as well, in the topic of power electronics. His current research interests include power electronics, electrothermal modeling, optimization of high-frequency magnetics, and development of energy storage-coupled power electronic solutions. The main objective of his research is to study the new solutions for the maximization of the energy efficiency for the next generation energy transition. He has supervised 5 PhD students, he has published 14 JCR journal papers and over 40 conference publications, and he has developed 3 patent proposals. Please, Igor and Josu, the floor is yours.
Good morning. My name is Igor Baraya-Chaburu. Joshua and me will be talking about the past, present, and future trends in power electronics. I will focus my presentation on the evolution, on the history of power semiconductor devices, since they are this history is very related to the evolution and development of power converters. Josu will be talking about the relationship between the University of Mondragon and the power electronics, achievements and future challenges. A power electronic converters transform electrical energy, satisfying specific needs of the application. A rectifier can be a converter can be a rectifier, a DC-DC converter, and so on. And of course, depending on the application, maybe we need the bidirectional behavior of this converter. If we want to connect the input-output terminals of several converters, maybe we need some galvanic isolation, even for safety reasons, maybe we need some galvanic isolation. Power electronic converters today are using generation, energy transport, and of course in the final application. Year by year, the amount of installed power electronic converters is increasing, and if we want to improve the efficiency of these systems, of course we need to improve each part of the power converter. Basically, we can say that a power converter is based on switching power devices in order to achieve high efficiency levels. Of course, that a converter needs some passive elements to for filtering purposes or even for the DC link. When those elements are operating, of course, that we have some power losses and we need some cooling systems to keep the operation temperature low. For monitoring and controlling purposes, of course, that we need some current, voltage, or temperature measurement. And finally, and not less important, of course, that we need some microcontrollers to implement the modulation and control strategies. Due to the relationship between the development and evolution of power electronics, I will focus my presentation on the history, the development of power semiconductor devices. To be honest, I don't know when the idea of power electronics arose for the first time. We have a look to the beginning of the last century. The mercury arc rectifier was already invented. It was used in battery chargers and railway applications. In 1957, the thyristor was invented, and this is an interesting milestone because it was the first time that in real power applications a semiconductor device was used. If we have a look to the thyristor structure, we can see that this is a 4-layer semiconductor device with these 2 transistor equivalent circuit. If we want to understand how it works, we can assume that this device is under forward bias conditions, and if we inject an external gate current, we can see how the load current, the main current, can circulate through the mains of this device. In this context, an additional or an internal gate current would be set inside the thyristor. Of course, if we remove this external gate current, this internal gate current would keep the thyristor in the on state. And this is an interesting positive feedback mechanism. If we have a look to the output characteristic of a thyristor, we can see how it can block voltage in the reverse and forward bias conditions. In the forward bias conditions, if we apply a positive gate current, we can see how the thyristor can conduct the load current with a very, very low voltage drop. This is nice. And if we need to switch off again the thyristor, basically, we need to drop the load current below a certain holding current. This is why, historically, thyristor has been used in line commutated converters, something like that, in which the generated energy has been or is transported in a very low to a very low distance using line commutated converters. The positive feedback mechanism of a thyristor has 2 small drawbacks. First of all, in case of short circuit conditions, the driver cannot detect any short circuit in the thyristor, so some other measurements should be taken into account. And in the other hand, the thyristor cannot control the current derivative during the switch-on process. And this is why modern IGCT devices need, for example, an external clamping circuit to protect the freewheeling diode. Even if the MOSFET was invented at the end of the 50s, the power MOSFET was introduced to the market more or less at the beginning of the 70s. At that time, the GTO, the gate turn-off thyristor, was already invented, and the power MOSFET was introduced to the market. This is an important milestone because if we think about the converters we know today, or we use today mainly, basically this is DC-DC converters, active rectifiers, and so on. All of these converters need some fully controlled devices. And this is why this year is quite important in the development of power electronics. If we have a look to the MOSFET, basically we can see that it has a quite simple structure, an entry layer, a P layer. We have a drain and source connected in each side of the semiconductor device, and the metal gate is isolated from the body of the MOSFET by means of some silicon dioxide. If we look at the symbol of the MOSFET, we can see how the MOSFET has an internal body diode. This body diode basically is the consequence of this PN junction. And this is interesting because in order to operate the MOSFET in the third quadrant, we don't need any additional diode. Sometimes you will see how the manufacturers prepare this diode to be avalanche proofing. And this is nice because in addition to the operation in the third quadrant, we can use this body diode for protection purposes. If we want to switch off a MOSFET, basically we should apply a positive gate to source voltage. In this case, we are generating a conduction channel below the gate terminal, and electrons can flow from the source and to the drain, or to the drain to the source. Okay, this is a bidirectional electron channel. Note that the gate terminal is isolated from the body, and that means in order to keep the MOSFET in an on or off state, we don't need energy because the gate terminal is isolated. We only need some amount of energy to change the conduction state of this device. If we have a look the real waveforms of a MOSFET during the real operation, we can see how we can fully control the switch on process, and of course, as the MOSFET is a charge control device, we can control the speed in which this transient happens. This is nice because if we have a look to the MOSFET is a quite fast device, so the energy we are dissipating during each switching transient is quite small. And that means that we can operate the MOSFET in a quite fast, with a quite high switching frequency. And that means that we can get a good trade-off between efficiency and passive elements module. One of the most important drawbacks of a MOSFET is very related to the blocking voltage of the device. Basically, during the blocking voltage, if we need to withstand this drain to source voltage, we can see how this reverse bias PN junction is the responsible to withstand this voltage. Basically, if we apply a certain drain to source voltage, we can see how the electric field penetrate into the resistive end region. If we increase the blocking voltage, we can see how the electric field dips or penetrates deeper in the end region. And that means if we need a high voltage MOSFET, we need a quite large device structure. Of course, in this case, the on-state resistance is quite worsened, and this is why today it's quite difficult to find silicon MOSFETs for more above 1 kilovolt with competitive on-state resistances. Basically, in this context, at the end of the 80s, the IGBT was invented. Indeed, at the beginning of the 90s, more or less, the IGBT module, the power module, was introduced to the market. And if you have a look to the structure of an IGBT, is quite similar to the structure of the power MOSFET. The main difference is here in the collector side, P extra layer. Basically, in an IGBT, we have a collector, we have an emitter, and we have a gate terminal basically isolated from the body of the semiconductor device. In this case, if we want to switch on this device, we have to apply a positive gate emitter voltage, and we are creating the conduction channel below the gate terminal. In this case, electrons can flow from the emitter to the collector. However, if we inject some electrons to the additional P layer, the P layer is going to inject some holes to the body of the IGBT. And these electrons will circulate through the internal PMP transistor. You can see how, in this case, we have electrons and holes as charge carriers. And you know that if we increase the amount of charge carriers, the conductivity of the device improves. And this is why the IGBT is a good device in order to operate at medium-high voltages without sacrificing the conduction characteristics. If we compare the output characteristic of a MOSFET and an IGBT, we can realize that even that the IGBT has an extra or it has a threshold voltage due to the extra PN junction, basically when the circulating current increases, more or less close to the nominal current, for example, the IGBT is a quite better conduction device than the MOSFET. Okay, so this is good. If we compare the switching behavior of a MOSFET, basically we can see how during the switch off process, basically the MOSFET has an additional tail current. Of course, this increases the power losses compared to the MOSFET. And we have another issue related to the switching behavior is that depending on the generation, IGBT generation you are using, you will realize that the switch off current derivative is not cannot be easily controlled by means of the gate resistance. This is important because if you have, for example, an excessive overvoltage during the switch-off process, and if you want to change, if you want to increase the gate resistance, you will realize that you are increasing power losses, but your problem, the overvoltage, remains in the circuit. So it's not a good idea. If we think about the IGBT, basically the silicon IGBT, basically we can say that this is on the top of power transistors, basically because it has the higher voltage current operating limits. The body of an IGBT doesn't have an internal diode, so we need to add an extra diode to this power module or transistor. If we want to drive this semiconductor, we need a gate driver. Basically, the gate driver is the interface between the input signal, the command, and the gate terminal of this device. It's important to understand that the IGBT was introduced to the market more or less 40 years ago, and it has been historically been operated with a gate voltage of plus minus 15 volts. If you have a look to the modern silicon carbide MOSFETs, for example, and the first silicon carbide MOSFETs, you will realize that at the beginning, the MOSFET was driven with plus 20 volts. And today, thanks to the development of silicon carbide MOSFET, basically silicon carbide MOSFETs satisfy the same standard imposed by the silicon IGBT, plus 15 volts minus 8 volts. Okay, so this is a standard set by this device. Of course, the IGBT is a transistor, and as a good transistor, if we operate this device under short circuit conditions, we will see how it desaturates. So the driver can detect any failure, any short circuit condition in the operation of this device. So the driver can open or can try to open this device if it detects a non-normal behavior in it. During this process, opening a short circuit, if we have an excessive overvoltage, quite simple active clamping circuits are quite suitable to limit the maximum collector emitter voltage to protect the device under short circuit conditions. And of course, and finally, it can communicate it to the control system to inhibit the converter. And depending on which position we are operating this IGBT, the driver should supply some galvanic isolation. Okay, and this simple structure is quite important because each time we think about a converter and we figure out this converter with an ideal switch, the real equivalent circuit, the real equivalent of this ideal switch is basically this figure. Okay, this transistor, this diode with a single gate driver. Okay, so this is an important scheme for power electronics. Probably you have listened that power semiconductor devices, silicon power semiconductor devices, can be manufactured without any defects. And that means that the operation and efficiency limits of current silicon devices are imposed by the silicon, not by the technology. This is why some years ago, some decades ago, manufacturers start looking for new materials in order to improve the power semiconductor devices. Of course, I'm talking about the wide bandgap materials. And if we are talking about wide bandgap materials, we are talking about the silicon carbide and of course the gallium nitride. Okay, so it's nice to see that at the beginning of the century, the first Schottky silicon carbide diode was introduced to the market. Okay, and it's nice because during the last 20 years, we have been more or less in the era of new devices that are improving the quality, the efficiency, and the volume of our power converters. Okay. In order to understand the real meaning of wide bandgap material, let me put you an example talking about, for example, the silicon crystal structure in which in this material we have, for example, the valence energy band and, of course, the conduction energy band. An electron can be in the valence band and can be in the conduction band, but never between them. This is the band gap, okay? If we have a look to the electrons in the valence band, electrons in the covalent bondings, basically we can see how if we apply external energy to this structure, for example, thermal or electric field, some electrons, for example, this one can get enough energy to pass from the valence band to the conduction band. Okay, and in this case, we have a free electron in the conduction band, this is okay, but we have the lack of an electron in the in some covalent bondings. Okay, so we have a hole. If we provide more energy, you will see how more and more electrons will get energy to pass from the valence to the conduction band. Okay. Why this is a problem? Basically because if we think about this structure as a, for example, N-type silicon structure, you will realize that in an N-type silicon structure, the amount of electrons is already high. So it's not a problem to have more free electrons. The problem is that in an N-type structure, we need a low population of holes. And when we have increased the amount of energy supplied to this structure, the amount of holes, the whole population has increased. So the electrical properties of this N-type structure is different, has changed. And this is why the silicon cannot operate at very high temperatures or very high voltages. If we compare it with, for example, silicon carbide, we can say exactly the same. We have the valence band, we have the silicon, the conduction band, and of course the bandgap is wider. So we have a wide bandgap semiconductor here. We can say exactly the same. We can put our attention in the electrons from the covalent bondings, and we can apply an extra energy. For example, this electron can reach the conduction band. Okay. If we supply more energy, we will see how the amount of electrons is not the electrons in the conduction band does not increase. So this is why, for example, silicon carbide can operate at higher temperatures and higher electric fields. Okay. The first silicon carbide device was the Schottky diode. Basically, a Schottky diode is composed by an anode, a cathode. The anode, the cathode is joined to the body of the diode by means of a resistive joining, but the cathode is joined to the body, to the structure, basically by means of a Schottky contact. And this Schottky contact is an interesting contact because it allows the current circulation in one direction, not in the other, so it behaves as a diode, and the voltage drop when the current is circulating through the diode is very low. Okay, it has a low threshold voltage, low voltage drop, so it's an interesting material. I'm sure that you have listened how a Schottky diode does not have a real reverse recovery current. Okay, but in order to reduce the leakage current during the blocking state, manufacturers usually introduce some P layers in the structure of this Schottky diode. Under the forward bias conditions, if we forward bias these PN junctions, you will see how during the turn-off process, the reverse recovery current is compulsory, is mandatory in order to remove the charge carriers introduced by these PN junctions. So we can measure some reverse recovery current. Even if this is not an ideal structure, is far better than all PN silicon junctions. Okay, so this is a good switching and conducting device. Okay, if we compare, for example, I'm sorry. If we compare, for example, a silicon carbide device with a silicon device, you can see that during the blocking state, for example, a silicon carbide device can block with a short length a quite high electric field. Okay, this is the real picture. And if we compare it with the equivalent silicon device, we can see how in order to withstand the same blocking voltage, the length of the structure is quite larger. That means that the silicon structure has worse conduction and switching characteristics. This is what wide bandgap devices benefits power electronic devices. Okay. And finally, what about gallium nitride devices? Basically, first of all, in my opinion, if we have a look, for example, to silicon or silicon carbide devices, you will realize that the good conduction and switching characteristics rely on highly doped PN layers. However, in gallium nitride, the idea is quite different. In gallium nitride, to put it simple, in gallium nitride, basically we have gallium and nitrogen atoms, and they are joined together by means of covalent bondings. Okay. The problem is that the nitrogen has a higher electronegativity than the gallium. So electrons in the covalent bondings are closer to the nitrogen than gallium atoms. And that means that in this structure, in this general structure, we have a certain polarity due to the electronegativity of these atoms. Okay, this is the basic idea. This polarity appears. If we have a look to a real GaN transistor, you will realize that a GaN transistor is composed by a gallium nitride layer and an AlGaN layer, aluminum GaN alloy. Okay, basically this is the AlGaN layer. The thing is that the polarity of the AlGaN layer is higher than the polarity of the GaN layer. Okay, so in the junction of both layers, basically we have a positive net charge. Okay, something like that. This positive net charge attracts all the free electrons from the body of this structure. So in this junction, we are going to see how free electrons are attracted. Okay, and this channel we are creating with the attracted free electrons basically has a high density and high mobility. And this is what we know basically like as the two-dimensional electron gas. Okay, this channel, this is a very good conduction channel. Okay, and this is the two-dimensional electron gas channel. Okay, what's going on with a real GaN transistor? If we have this structure already, basically, in order to manufacture a real transistor, we can add a source, a drain, terminals, and a gate terminal. Okay, and this is the most simple GaN transistor available today in the market. It has two problems for power electronics. First of all, this structure is a lateral transistor. And as a lateral transistor, the problem is that if we need to block more voltage, we need a wider device structure. So we are worsening the on-state characteristics. And this is why today gallium nitride devices are up to pure gallium nitride devices are up to more or less 600 volts. Okay. The second problem, as you can see here, is basically that between the source and the drain of this structure, we have already created a conduction channel. This two-dimensional electron gas channel basically exists without applying a positive gate voltage. So this is a normally on transistor. And you know that in power electronics, normally on transistors are quite problematic, particularly when we energize for the first time the converter, or when the gate driver loses the supply. They tend to provoke short circuits. And this is why today manufacturers are introducing to the market new GaN transistor structures with some modifications in order to cut off the the free electron channel in the absence of a positive gate to source voltage. And this is how manufacturers are introducing to the market normally off transistors. The problem in today, it's the reality of today gallium nitride transistors is that on the one hand, the gate threshold voltages of these transistors are quite low. If you have a look to the datasheet of a PGAN or a JIT transistor, you will realize that the gate threshold voltage is not high. So some crosstalk problems can arise. And the second problem is that the gate driver structures required to drive these devices is different from the standard set by the IGBTs. So you will see how, for example, a JIT GaN transistor has a quite different gate structure if you compare it with the typical IGBT driver. Okay, so let's see in the future how it evolves, how the development of gallium nitride devices happens. And finally, this is the last slide. Here you have the IGBT. The IGBT, we can say that the IGBT is on the top of power transistors, basically because it has the higher voltage and current limits. Okay, but you can see how the operation switching frequency is not too high just because the power losses it generates during the real operation. And you can see how, for example, silicon carbide MOSFET and diodes doesn't have a large operation limits. It has less blocking voltage capabilities, for example, but they are quite efficient switching. So basically, you can see how in certain applications, the silicon carbide devices has substitute IGBTs in order to increase the switching frequency, achieving the same or even higher efficiency levels. Okay, this is what wide bandgap devices provide to the market and benefits power electronics. Okay. So I don't know if I'm on time. That's all. Thank you very much for attending. And vale, va. Venga.
Okay. Thank you all. So it's my turn. So I'm going to present a little bit which is the past, present, and future in power electronics, but from the point of view of our university, from the University of Mondragon. Okay. So the index that we are going to follow, what's power electronics, or what do we think, no? That could be power electronics, and how we are structured in the University of Mondragon regarding this, no? The past, present, and future. And you can see that I will divide it in 4 main topics that all of us that we work in power electronics have been focused, even nowadays and also in the past. And finally, some small conclusions of where we are going, okay, and where do we want to go with all together in that sense, okay. So when we start with power electronics, people especially thinks in the power semiconductor, and I think that that's maybe the core, no? The core of the power electronic converter. So start thinking of IGBT, MOSFETs, as Igor has presented, going to wide bandgap devices like SiC and GaN. Okay. Okay, but the core is true, it's the power semiconductor. But we all know, or we think, okay, that it's a really very intensive and multidisciplinary job. Okay. So all of us that we work in this job in power electronics, okay, we have been working in the PC, okay, we have been doing software issues, we have gone to hardware, no? We want to measure, we want to check whether PC work is the same as our after hardware work. We go to labs and we love testing, checking what's happening, and of course, finally, we have to go to the field. Okay, so we have to go to application. This is mainly what we understand in a brief part. For sure that there are a lot of more, okay? What we understand for the point of view of a power electronic engineer. No? In that sense, in our university, we have a research line, the energy research line, that we have a combination of 3 different research groups. Okay, we are mainly like 40 researchers, 30 of them we are doctors. Okay, with 2 new ones now, so we should change this to 32. And in this moment, from this week, we are happy in that sense, and around 15 PhD students that are one of the main courses that we have in a university. Regarding the 3 research groups, we have very active group in electric machines and drives. Okay, the power electronics at itself as a group, and of course we can't forget now about the group of energy storage system that is one of the most important parts nowadays. Okay, what about the university? Okay, if you take our university mission, okay, and I take it as a sentence, okay, the mission of our university is to transform the society. Okay, so if we take it like that, I think that in the power electronics job we can do it. Okay, first, we are teachers. Okay, we are teachers in our university. Okay, so we have to transfer to students. One of the best examples is the previous presentation of Igor. Okay, it's a perfect teaching idea, no, of how a semiconductor works, where is the technology, how to use it correctly, and this is a big part that we have to do. Okay, in that sense. And the second, we are researchers, so we have to transfer our knowledge to the industry. Okay, and that's one of the second parts. Okay, so that's our mission, and how can we work in power electronics in that sense? Okay, in the present and also in the future. Okay, regarding teaching, now we have 3, we will say, power electronic campus. Okay, our headquarters that is located in Mondragon, as the name of our university. Okay, the campus here in Hernani. Okay, in installations of Orona Ideo next to San Sebastian, and the new campus of Bilbao. Okay, where we actively work in 3 of them in power electronics. Okay, and regarding industry, okay, well, the transfer. I have just a slide of some of the industry partners that we have. Okay, and a lot of you are attending here to these presentations. Okay, research centers where we collaborate, and universities. Okay, and in recent we can have some of them. Okay, even from the US and from Denmark. Okay, during this presentation. So we have close collaboration with industry research centers and universities. Okay, it's a main part. Okay, we can't be alone in this power electronics work. Okay, so the idea about past, present, and future of our university in power electronics, I'm going to try to make a small resume. Okay, we have a lot of things, so I give you some ideas regarding. So I will give a view of like a timeline. Okay, so a fast timeline of what we have done, or what I understand we have done. Okay, in power electronics. Okay, in the past, present, and future, in 4 main topics. Okay, regarding software, what are we doing in simulation and modeling? Hardware, what are the designs and measurements that we are doing? What capabilities we have in validation? Okay, and which are the applications? Because in this university, as Roberto said in the previous part, we love to go until the final part. Okay, so the going to application. So past is a good question, and when I was preparing, I asked, where do we come from? No, mainly if I take our group, I will say mainly we are electronic and automation industrial engineers. They are the big part of our the researchers and lecturers. We are this part. So we are a mix. Okay, as Professor Andersen says, control engineers. We are a mix between power electronics and control engineers. So I think that it's a good mixture. Okay, in that sense. But where it comes our passion, I will say, about power electronics. Okay, so here is a good example. We have had in our university one of the biggest pioneers, okay, in power electronics. So these are some applications in 1985. Okay, they were able, okay, to develop hybrid renewable systems with PV and various energy sources, hybrid trucks and vehicles in the 1994, and even an electric vehicle, okay, that was fully operable in 1996. So I think that they are a big part of why we are here, no, and why we are all here. So we only have to give thanks, okay, to these pioneers to to be part, no, of why we are here in this sense. Okay. So starting with software, no. So it's something that we always try to do. Okay, we develop a model. Okay, you have the model, and after you have to perform the simulation. There are two different topics. Okay, that could be they are closely coupled, but they are very important to do. Okay, so I will give some tricks, simulation topics. I think that the students that are here know me that it's very different to work in the transient world. If we want to go to steady state, okay, things, or to use analytical tools, we love to do them, but they are also electrical simulators or modeling options. No? So we have to be able to combine all of them in that sense. In the past, and this is a good reference, okay, our group has, I would say, suffered in some senses with one simulator work. We were in the earliest with Saber, okay, and a lot of people here has used it, and we have had some hard days, but it was our preliminary part in that sense in the past, okay. And where are we in the present? Okay, so we are mainly working with tools of MathWorks Simulink, okay, as our main simulation tool, and we have developed a lot of power electronics electrothermal models. So we have done different simulation models, working with different accuracy, fidelities, depending on the application. So in that field, we are active and we have a lot of issues. Okay. We also work with spice-based simulators, LSpice and others. Okay, when we work to analyze the dynamic behavior. No, so when you start thinking of how the switch, the device switches, or EMI analysis, so we also use other type of simulators. Okay, and also we are engineers and we want to obtain the analytical equations. No, so we work hard in analytical modeling, and even we have a good reference inside a book. Okay, inside our university. Okay, in that analytical modeling of power converters. Okay, so where are we going, or where are we now? We're trying to go. No, we are developing a hard work in own simulators. Okay, in simulators and tools, I will say. Okay, so one big progress. Okay, we can say we have a tool that is called C-Step. Okay, it's a registered software. So really good work in our team. Okay, so as Dr. Leon Tolbert, okay, explained for us, we have agreed that we are integrating out of power electronics. Okay, so we have a tool, okay, to analyze the stability, okay, for electric power systems with a high penetration of electronic power converters. Okay, so this tool permits to our research and to the industry, okay, to know how it's going to behave the grid with this high power integration of the power converters. Okay, we are developing also analytical simulators for transient simulation. Okay, equivalent to an SPICE, but just under control in our state space modeling. Okay, we love it also in that sense. So we have also this type of tools, and also we are just shipping to multi-objective simulations tools, where we think that it's very important to have a high database, okay, of the different manufacturers, not only semiconductors, heat sinks, cores, everything inside, just to analyze that to design a converter is a compromise, not only of the semiconductor, all of the passives, cooling system, anything, even the cost. Finally, when we go to the industry, they ask us, I think not the last question, the first question, how much is the cost of this system? So it's something that we have to insert in the loop. Okay. Okay, and regarding modeling, so we are developing also ultra-fast steady-state simulators based in frequency simulators. So it's interesting, okay? We don't need to go into the time domain. We can go to the frequency domain, obtain the frequency domain analysis, okay? And after change it to the time domain, okay? And that gives a big opportunity when you are designing and you want to obtain steady-state signals, okay? To be able to analyze different structures in a very fast way. We are developing tools also to analyze the impact of the power electronic converter in all the system. Okay, so Dr. Anchona Arrizabalaga, okay, in his PhD, has presented a tool, okay, where we are analyzing the levelized cost of energy, okay, and the impact, okay, of the power electronics in the increase of that energy, okay. And for sure, it's something that is starting to sound. It's not only power electronics. It's going to be, and it's been energy electronics. Okay, so we have to forget about the power loss. We have to focus on the energy loss in a mission profile or in an application. So this is something that should be inserted from the design also point of view that should be covered, and we are covering in that sense. So it depends on the mission profile on the application that you have. That also depends for the application design. Yep. Okay, so regarding hardware and measurements, if we want to validate our simulations, okay, so classically, the hardware design has been highly dependent on semiconductor technology and power range, as the last slide of Dr. Igor. Okay, classically should be a compromise. Has been a compromise between the switching frequency and the output power. Okay, the biggest trade-off. And here we have in our university we have made designs from line frequency or line commutated converters to low medium frequency, and we are reaching now the high frequency. And when analyzing measurements, I think that all power electronics we have been focused in efficiency and power losses, and having always how to measure the efficiency, the power losses, conduction, switching has been and is going to be, in the has been the past and is the present and will be the future, how to obtain these values. So a little fast timeline about this in our university. Okay, regarding measurements, we use them, or we have one work classically with bad methods, okay, and obtaining the system efficiency between the input and the output. And for sure that we have done more than once, okay, testing, double pulse testing to obtain the switching losses, okay, that classically has been a must, okay, so for a power electronics engineer. So we have different test benches for this capabilities, for as an example of a 2 kilovolt 1000 amperes double pulse testing system. So has been the past. I think that is going to be the we use it in the present also, but was in the first step. Of course, that to measure these systems when the efficiency is high, and second, when the devices are fast, it's not so easy, So where are we going? Okay, so not so easy to measure accurately, and that's a good name, accurately, because you can measure, but you have to be sure that what you are measuring is correct, and that's much more difficult than measuring. Okay, and second, you want to measure in a, we will say, in a similar layout, or even if possible, same layout that we are going to have in the final converter. Okay, and with low or zero invasive methods. Okay, not changing the behavior of the converter. Okay, so here we have a very good publication and very good results. Okay, so when analyzing the switching behavior, and thanks Dr. David Garrido. Okay, how to measure this type of switching losses. Okay, with low insertion losses and also low cost, because this equipment classically is very expensive. Okay, and regarding the conduction behavior during switching, okay, we are also finding things that I have heard, that dynamic RDS on in GAN and everything. Okay, we are focusing on that, and I think that it's something that where we have to work in the present and future. Okay. Okay, but what happens if we can't measure? GAN is going fast. For sure that in the converter that Professor Andersen presented, he was not able to measure the voltage derivatives and currents of this small system. What can we do? Okay, so there is a relation between the power losses and the temperature. Okay, so if we can measure the temperature, we can have an image of how much are the power losses. This is the main idea, without inserting any invasive system and even in the same layout. That's the objective that we have now we are working in the present and will work in the future. Okay, so we have developed a methodology where we parameterize our system with different power losses. Okay, so we obtain, the first step is to obtain a good thermal model of our system, and after we develop a validation test where we can calculate the idea if we measure the temperature and we know the losses. So measuring the temperature could be very useful to know the losses of the different devices in different working behaviors. Okay, imagine a 0 voltage switching nearly 0 losses. Okay, but we can do things, okay, to calculate them from a temperature point of view. Okay, we are increasing the complexity of this because in some converters, the power losses of the semiconductors could not be mainly the main ones or even only the only ones. Okay, so we have focusing problems with the paths. So traces and paths, current paths, the resistance is not 0, and we are focusing problems, and we are increasing the complexity of our thermal model to insert them in the thermal modeling part. Okay, we have used these techniques. For example, something very interesting that was the dead time that we listen, which is the optimal dead time, no, for working a converter in soft switching, no. So thermally, it's possible to check it. You go for a high dead time, you go down, down, down until you start going to hard switching or incomplete soft switching, no. So we can check it. We have checked it also thermally. It's interesting, no. It's not only to measure electrically that you could insert something inside the circuit, but you can measure it thermally. So are interesting topics. Okay, and the last one, be careful with the test bench that you have. So we have analyzed that the test bench that you have, the thermal model changes during during you are doing tests. So you have to recalibrate it or take it into account. Okay, so we have 6-day tests, we will say, and in the last day, the test bench was not equal to what we have it in the first day. So changes, no, the thermal behavior of the test bench. So interesting topic that will be some of the focus in the future. Regarding hardware, okay, we did in the past a lot of line frequency converters. One of the ideas, a 500 kilowatt programmable DC power supply and more. Okay, a lot of different topics. In the medium frequency converters, we have a lot of prototypes. Okay, in that sense, in our university, oriented to high power. Okay, from 3-level MPC converters and with 1.2 kilowatts, 50 kVA. 5-level cascaded converters, okay, and even 4-level MPC converters in those I will say medium frequency range converters. So we have demonstrators that we can use after for different applications. Okay. Regarding hardware, where are we going into the future? I think that this sentence about modularity is very important. Okay, we think that a single conversion unit, if you want to make a megawatt converter, which is the optimal conversion unit? Should be a 1 megawatt processing converter, or it could be 500 kilowatt, which is the optimal, no? And this is something modularity that should be inserted in the loop, okay, of the design process, and we want to be there in that sense. Of course, we are focusing the high frequency design, okay, with wide bandgap devices, with SiC and GaN, with high switching frequencies and high DVDTs and DIDTs, no? So some examples, okay, of a GaN-based converter design for an industrial application with a isolated DC-DC, okay? That was an update for a silicon behavior. And a must that these high frequency issues should be inserted from the first design process. And this has been something that we have not done in the past. So after the problems came, okay, when you were to certify something with EMI or anything, if you haven't taken it into account, so you have problems. So we are also designing methodologies, okay, so to design the converters with this EMI-oriented type of design, okay. And yeah, power electronics and hardware, it seems converters, but high focus in passives and especially in magnetics. We have discussed during these days a lot, and we think that is one of the components that is the key component nowadays in power electronics. So in the past for us was we designed an inductance value, temperature range, try not to be losses, and we just keep it outside and they give one magnetic and we don't even know how it works. Okay, so that must be inserted in the whole process of design of the converter. Okay, so one magnetic component could give you one semiconductor or one switching frequency. With another one, you can have another optimal switching frequency, which is the optimal design from the point of view of the system. So that should be inserted in the loop. Okay, and the other one is that the data sheets that they give the magnetic vendors, okay, are not sometimes useful for power electronics. Okay, we have sinusoidal waveforms, frequencies out of the range, so we need to test this passive. So we are generating a database, okay, regarding we generated an automatic core loss and thermal modeling testing platform where we can control different variables inside the magnetics, and we can test the magnetics and obtain data, okay, with some converters that can go to excite these magnetic components until the range of the mega range. So something that where the power electronics is going, okay, and we have also facilities, okay, to develop different type of magnetics in a, I would say, in a semi-professional way, no, not on a low prototype capability. So I think that we have to work in that sense in regarding passive components. Okay, regarding validation and testing, okay, so it's important. We need labs. As power electronics engineers, we need a place where we have to test our prototype. So lab testing for validating the design is a must in that sense. And in this sense, we have test rigs, different test rig and platforms, and we also are focusing on new testing issues. In regarding validation and testing, in our university, we have several different, I will say, labs, mainly in Mondragon and here in Hernani, where we can test until low power, different equipment that we can use classically. And apart from these ones, okay, we had some, I will say, different labs, okay, that maybe are not so easy to find in other universities. Especially, we have a 4 megawatt medium voltage lab with different AC voltage and DC voltage configurable versions that where we have tested with the industry partners interesting or even high power solutions. And also we are going to platforms oriented to hardware in the loop. Okay, more and more, even the industry partners are changing, not testing the controllers against the real power electronics. We can do a hardware in the loop model of this power electronic to test our controllers. Okay, and also something that has been presented also, how to test this if we don't have enough power in our lab. Okay, so we are developing testing platforms, okay, where we do zero power or only inserting the power losses, as Dr. Tolbert told us, okay, power rings where we insert only the power loss, and we can test the converters, even inverters or DC-DC converters in a real power range or application. Okay, what comes in the future? Okay, so we have focused in power hardware in the loop. Okay, so a device or a converter, okay, that emulates, okay, our physical grid, anything, okay, but with a power sense, not only the hardware in the loop, okay, also it generates the same waveforms, okay, as that we have in the real application. And new needs, it's good to say there are new needs, so we have also focused on new labs. Okay, so we have nearly finished, I will say, okay, a new lab going upper in power until 10 megawatts, for especially focused on the new generation of wind turbines to test different equipment or different converters that are connected to the grid in that sense. And also we are focusing on having some labs, okay, where we can do advisory work and pre-compliance oriented work, okay, regarding the EMI and EMC. Okay, and finally, I think that the biggest part, no, application. So we, as a university, the Mondragon University, we have high focus on on-field validation and real power testing. So it's something that we have worked a lot, okay, and we have high number of projects and demonstrators in different applications. So there are some of them here, but there are much more that we have done in the future. Okay, so regarding applications, okay, I have to value two colleagues that are today here with me. So regarding to high voltage and high power converters, I would say that they are impressive demonstrators. First one, Dr. Igor Barayecheburu, okay? He made a lot of years ago something impressive that was a series connection of 3 IGBTs. And we are in the university really proud of what he developed a lot of years ago. So it's something that was very important. And also my colleague, Dr. Mikel Mazuela, okay, so with a high demonstrator in close collaboration with Ingeteam, okay, of a 5-level MPC converter in the range of 1.5 megawatt. So we have go to the field in high valuable and high power conversion ratio. So I think that is something that we have to take into account in that sense. Regarding applications, so we have also high focus on thyristors, no? So Igor says was one of the preliminary technologies, but it's here also in some applications, and we have done interesting things, and we are doing interesting things with thyristors nowadays. So we develop applications of a static, like a static switch, okay, with thyristors for high-speed trains. So we develop a static switch that can withstand a 52 kilovolt AC grid, and even can fit a 12 megawatt train in continuous operation. So it was tested also in a real application in this case in a railway just next to Sevilla. Okay. And the second part of with thyristors that we are working hard, okay, are the topic of electronic tap changer, okay. So modifying the voltage of a transformer, okay, by changing the taps of the transformer, not in a mechanical way, using thyristors and giving high dynamics and flexibility to the grid. In that sense, that could be really useful, okay, for the imbalances that we are going to focus in the grid during the next years. Okay. Application regarding, we have, I want to mention 2 applications. Okay, we have a lot of them, but in the present that I think that having good achievements, okay, regarding the EV charging issues and renewable. Okay, so here we have to do a efficiency push, okay, but of course it's a trade-off with system cost, but it's something that efficiency should be increased, okay. And here we have the thesis of Dr. Anchon Arezabala, okay, with some very interesting demonstration for PV or wind generation, and taking the advantage of just proving different technologies and multi-topologies, 2-level, 3-level, okay. Also, we are very proud, okay, some final prototype of the thesis of my colleague, Dr. David Garrido, okay, it was a fast EV charger, and we have to say that in 2020, okay, was installed in here in the Basque Country, and was the fastest installed charger in Europe in the 2020. So it's also something that we are really proud in that sense. Okay, and we are also finding other alternatives, PPC modular fast EV chargers. Okay, has been a great, very big contribution of the recent Dr. Jon Alzola. Okay, with efficiencies above 99% in a very high state of charge change in a battery system. Okay, and also we are pushing the technology for other technologies, no? So we have developed a wireless charger, okay, around 50 kilowatt and 80 kilohertz. Okay, all you can see 4 of them, or 3 of them using silicon carbide technology, and 1 of them using silicon technology. So where are we going? Applications with the applications in the future. Okay, so we have to push. Okay, in some applications, that's our idea. Okay, hydrogen generation, it seems that is coming. So we have different solutions and different ideas in that sense, where we are working with partial power converters and comparing high power solutions based on thyristors with classical IGBT solutions. We have to push in power density. So it's a topic that has been focused here in this workshop. Okay, there are applications where they are asking that. Okay, audio amplifiers is one, but servers, renewable, EV are pushing in that sense. We have to be smaller and continue being efficient. Then we have different ideas. PCB technology is changing. We have different substrates, ceramics. The chip is starting to go inside the PCB. So it's not that you buy a discrete. Inside the PCB, you can have the die. So are things that we are focusing GaN is coming and well, it's here, and that's in some senses. Cooling systems, there are advanced cooling systems that we have introduced in the world of power electronics and also magnetics and topologies. Okay, reliability is an issue that should be a must for industry. It's a must. No, it should be, and we are starting working on that. Prediction issues, life estimations, how finite element models regarding thermal cycling, what's happening inside the module. So we have different topics where we are covering in that sense. Okay, and finally, specific applications as avionics. Okay, so we know we are listening, more electric aircraft or electric aircraft. Okay, so we have done some prototypes. Okay, in some range where we have to push also the technology in these issues. So as a brief conclusion, okay, power electronics, yes, it's true. The core is the power semiconductor, no? That's where we come from, but we are more multidisciplinary than ever, okay, in power electronics. So in the university, I will remark again, if you take the university, I ask to our rector and I say, director, sorry, and I say, which is the mission? Is to transform the society. I think that we are doing it, okay? So we have to transfer the knowledge to students and industry, and this slide is only to say that we are open to that. We are open to collaborate in that sense. And this is a fast timeline resume, going fast, okay? So if you need any more info, do not hesitate to contact us. So we have different options in that sense. And finally, I want to thank all the Mondragon University team. I will see more than team, they are friends, okay, for the support in this presentation. So thank you to everybody.
Okay, thank you, Josu. Thank you, Igor, for this nice presentation. I don't know if there is any question in the audience. It was very clear.
They are hungry.
Okay. What about online attendees? No questions. Thank you, Neko. Okay, so we have now a break for the lunch. It's waiting for us in the hall. We will be back for the last two presentations at 2 p.m. Okay? If you have anything, you can ask us. We will be there to help. Okay? Thank you. See you later.
Low down and dirty chain.
I would like to mention that I will also be presenting the introduction of the following talk by Dr. John Anzola. So after that, I'm going to be explaining some of the applications we have for the silicon carbide modules in high power. I'm going to present also the challenges that I think that we have to overcome in the future. And I'm going to show you some techniques in order to try to solve those challenges. Finally, I'm going to finish my presentation with some general conclusions on the future work I think that should be done in this field. So let's start with the introduction. Remember, not only of my talk, but also of the following talk of Dr. Anzola. So in a world in where the electric generation is growing drastically in the last years, governments and agencies are looking for an emission reduction plan, and the need to introduce renewable energies into our electrical grid. But for that, we need radical structural changes, such as distributed generation, transition to renewable energy, more electric transportation, such as trains, e-vehicles. Those are our hot topics nowadays. And finally, also energy efficiency plans. Why do I mention that last? Because there's an estimation that only 33% of the generated energy is finally consumed in our homes or industry or loads. So all the other energy is lost in the way from the generation to the consumption side. Those losses, of course, include generation losses, conversion losses, transportation losses, conversion losses again, and consumption losses. So we are going to be focusing during my presentation and Dr. Anzola's presentation on the conversion losses. As previously Professor Baraya has told us, there are different power converters, different power conversion stages that we can perform. And I will be focusing on the DC to AC conversion, which are called the inverters. And Dr. Anzola is going to be focusing on the DC to DC converters. As Professor Aizpuru has very well explained, we work on several topics here in Mondragon Unibertsitatea, trying to optimize these power conversion stages. Some of the main topics are, of course, the active semiconductors and the passive components, such as magnetics or capacitors. However, there are also other topics that need to be investigated and improved, more looking at the system level, such as topologies or architectures. I will personally be talking about the active semiconductors, wide bandgap semiconductors, but I honestly think that the semiconductor technology and transistor technology and structure is closely or should be closely linked to the topology and the strategy, or the switching strategy that you use in your applications. It's not the same to have silicon IGBT or a silicon carbide MOSFET, and the topology that we select should also not be the same. So I see a link between those two topics. And the following talk will be about specific architectures to improve the conversion efficiency and conversion performance of DC-DC converters at architecture level, about partial power processing converters. The presenter will be, as I said, Dr. Anzola. So without any further delay, I'm gonna make a very fast review of some topics that already Professor Baraya has mentioned before. However, he hasn't shown us this graphic, and I think it is very, very interesting. Here, I show the physical characteristics of the wide bandgap devices, such as the silicon carbide and the gallium nitride, normalized with respect to the physical characteristics of silicon. To highlight some differences, I would like to mention the higher breakdown electric field, allowing higher blocking voltages, higher electron saturation velocity, and higher thermal conductivity and bandgap energy, which are related to high temperature operation. As Professor Baraya said, in theory, silicon carbide semiconductors, for example, would be able to operate even at 500 Celsius degrees. However, nowadays, they are limited by the packaging that is used in these semiconductors. Focusing now our analysis on the gallium nitride transistors, we already know that we cannot build traditional vertical structures, so we have to build horizontal structures. They are called high electron mobility transistors. Here we can see the 2D electron gas, as Professor Baraya mentioned. These structures, which are depletion mode structures, lead to normally on devices, and these ones, which are the enhanced mode electron mobility transistors, lead to normally off devices. The better switching characteristics and the low loss of this electron gas lead to, better switching performance and lower losses. However, these novel structures, they generate an uncertainty, and remember that their blocking voltage is limited. So their high voltage application is very limited. However, if we focus our attention on the silicon carbide semiconductors, this graph should be familiar to all of you. We have traditional vertical structures, and we can create unipolar devices, silicon carbide MOSFETs, for blocking voltages in where traditionally silicon bipolar devices, IGBTs, are used. This leads to a better performance in switching with lower switching losses and a theoretical better higher temperature operation. However, using these devices has a system level impact, mostly in the cost, in the higher cost of the silicon carbide semiconductors. However, their high blocking their high voltage blocking capability together with the high temperature operation allows them and makes them promising in high voltage and high power applications. So this is what I'm going to be focusing now, the application of these semiconductors. Here I show you the very well-known two-level topology. It has two switches, and each switch has to block the whole DC link. However, it only has one switch in the main current path. It's a simple and cost-effective topology. However, as the switches have to block the whole blocking voltage, the switching performance of this topology is not the best. So we should use good switching devices in order to counterbalance the bad performance of the topology in switching. In the right-hand side, now I show you a multi-level topology, a three-level topology. In this case, the switches only have to block 1/2 of the DC link. So the switching performance of this topology is better. However, there will always be two semiconductors in the current path, increasing the conduction losses of the topology. In addition, it is more complex and it has a higher component count. So using the multi-topology and multi-technology platform that Professor Aizpuru has presented before, we have done some different analysis comparing silicon carbide and silicon semiconductors, as well as two-level and three-level topologies. Here I present the efficiency of the two-level silicon configuration. As you see, the efficiency is pretty low, even more if we analyze its performance when we increase the switching frequency at the maximum power point. So how can we increase the efficiency of this technology? Well, as we know, the silicon IGBTs are not good at switching. Professor Baraya has already told us about that. They are storing minority carriers and they have high reverse recovery. So we can implement topologies, three-level topologies, which favor this kind of bad switching performance. So taking advantage of the good conduction characteristics of IGBTs, we can overcome the conduction losses of the three-level topologies and increase the efficiency of our two-level simple topologies. As we are still using silicon IGBTs, the switching characteristics, even if improved, when we increase the switching frequency, the performance is not that good. Okay, what happens now if we introduce silicon carbide in this comparison? Well, it's a game changer. As you can see here, even using a two-level topology, being simple with low component counts, only 2 semiconductors per branch, remember, we improve the efficiency significantly by taking advantage of the good switching characteristics of silicon carbide. The two-level topology with silicon carbide, due to the good switching characteristics, is better than the three-level topology with silicon IGBTs. And if we analyze the switching performance of this topology, the two-level topology, we see that it's not highly penalized by the increment of the switching frequency. However, as Dr. Bhattacharya said before, there are some challenges that we have to overcome when using silicon carbide. And these challenges, of course, are related to their high switching characteristics. Their high switching speed is their main benefit, but also their main drawback. The fast switching is divided between high DVDT and high DIDT. The high DVT will excite capacitances in our circuit, generating undesired currents, and can lead to the false turn-ons, for example. If we focus our analysis on the high DIDT, it will excite inductances, generating undesired voltages in our circuit, and will cause overshoots. Dr. Aizpuru also said that the measurements should keep up with the switching speed of the semiconductors. We will now focus our study on the phenomenon related to the high DVDT. So the phenomenon we are analyzing now, it's the false turn-on. It is when you turn on accidentally a switch causing a short circuit. The phenomenon goes as follows. First, you turn on the high side MOSFET at high DVDT, and the other switch will experience exactly the same DVDT. Due to the equation 7 that you see here in the right-hand side, you will experience a current through the gate to drain capacitance in the off MOSFET. Some of this current will charge the gate to source capacitance, increasing the gate voltage. If this voltage goes over the threshold voltage, this device will be falsely turned on, causing a short circuit. Okay, how can we prevent this issue? Well, the first main thing we can do is, of course, try to slow down the device and reduce the DVDT, so we don't generate this undesired current. Okay, then we would be increasing the switching frequency and of switching losses, sorry. So we don't want that. Another thing that we can do is to supply negative voltage, as I show you here, in order to increase the voltage security margin in the gate. So even if we experience a voltage spike in the turn on of the opposite switch, this voltage spike will not surpass the threshold voltage and the device will not be turned on. Which is the drawback of this? Of course, we increase the complexity and cost of our gate driver. As Professor Bhattacharya said, active drivers are needed when using silicon carbide semiconductors. Focusing now on the phenomenon related to the high DIDT, we analyze the overvoltage. When a switch is turned off, it has to block the DC voltage and the overshoot caused in the total stray inductance of the power loop. This total stray inductance is caused or is composed by the inductance in the modules, the inductance in the capacitors, and the inductance in the bus bar or the connections. The final challenge that I mentioned before are the measurements. Why? Because the fast switching frequency, the fast switching speed of the silicon carbide semiconductors will excite even the smallest parasitic components in the circuit. So maybe introducing voltage probes and current probes will alter your circuit and will perturb your measurements. So introducing voltage probes and current probes everywhere in order to check the gate voltage or check the drain to source capacitor without thinking on the whole system has to end with silicon carbide devices. So what can we do in order to overcome some of these challenges? Here in the 5th chapter, I will present you some optimization techniques related to the power stage. Here I show you the well-known 3-level topology I mentioned before, which consists of 2 switching loops. The first one is the short switching loop, only composed by 1 module, and the other one is the long switching loop, composed by all the modules in our branch. However, if we focus our analysis on the short loop, we will see that it is a 2-level topology. So we can use this short loop to analyze also the 2-level topology. In my PhD, I present a methodology to test the 3-level. I present a methodology to optimize the power stage of 3-level converters for the use of silicon carbide. But I want to point out 2 key points. The first one is that we have to use low inductance components, such as modules or capacitors. And the second one is that we have to use the magnetic cancellation theory in our advantage in order to reduce the inductance on our power loop. So what is this magnetic cancellation theory idea? Well, when we have a connection, when we have a bus bar, that current path has a self-inductance, which is represented here. These are material, the properties of the material, and these are the physical characteristics of that current path. However, when there's another current path close to the previous current path, there's also a mutual inductance. It affects the previous one. So there's an interaction between the 2 current paths. So the final total inductance of the switching loop will be composed of the self-inductance of each current path plus the mutual inductance between them. However, as you see here, we have the cosine of the angle between the two currents. So if we make this cosine negative, we can use the mutual inductance in our favor to reduce the total inductance of the power loop. Of course, if we make the two currents totally opposite, 180 degrees, the total inductance of the the total stray inductance of the power loop will be the minimum. So we have tried to apply these concepts in an optimized power stage. And here I show you the first analysis of the short loop. Remember, only one module involved. In the left-hand side, I show you the testing of only a single capacitor, the short loop with only a single capacitor. And in the right-hand side, I show you the testing of the short loop with optimized capacitors. Two capacitors in parallel, optimizing their placement in order to force opposite currents. We measure the impedance of both switching loops with impedance measurements, and we see that we can improve the inductance of the switching loop, forcing opposite currents in between the capacitors nearly 80%, which is, of course, a better improvement, a higher improvement than only placing two capacitors in parallel. Focusing now our analysis in the long loop, remember, composed by all the modules, all the three modules, we have to make sure that the returning currents can overlap to the ongoing currents. So if we analyze here the optimized neutral layer, which overlaps all the other busbar layers, we can see that the expected current path is the following. As you see, the returning current perfectly overlaps to the ongoing current, applying opposite currents and magnetic cancellation theory. However, if we bypass this optimized neutral layer with a cable and we force the current through this cable, we will get this current path. As you see, none of the current is not allowed to overlap the ongoing current, so the magnetic cancellation theory cannot be applied. By using overlapping currents, we can improve the inductance of the whole switching loop over 80%. In this point, it's important to mention that the measured inductances for the short loop and the long loop after adding the modules are 22 nanohenry and 44 nanohenry. Keep it in mind. So now it's time to check the switching performance of the power stage. We have been performing measurements with the impedance analyzer. Now it's time to actually switch some amps. So we see here in the left-hand side, the short loop, the turn-off of the short loop, which is where the overshot is suffered. For the single capacitor in yellow and the optimized capacitor in pink. In the right-hand side, I show you the same turn-off for the long loop. Here we see that, first of all, we achieve our main objective, that is controlling the overshoot. We have a short or low stray inductance, so we can control the overshoot, even switching at very high DIDTs. However, we can also calculate the stray inductance of the switching loop with the switching waveforms. We did, and we saw that the measurements match perfectly for the short loop. Remember, only one module in the whole switching loop, but do not match for the long loop. Remember, 3 modules in the switching loop. So I'm going to finish my presentation with conclusion and some future work that I see that can be done in this topic. The first one is that non-relevant phenomenon for silicon IGBTs become key when designing systems with silicon carbide. We have to, again, optimize the layout and the switching loops in order to reduce the parasitic components in our power loop. A non-optimized design can lead to destructive failure, such as false turn-ons, causing a short current or overshoots. Or maybe we have to slow down our device in order to avoid this phenomenon to occur. However, we would be reducing the efficiency of our system and not taking full benefit of silicon carbide semiconductors. So the final conclusion, or the main conclusion regarding the challenges, is that the whole system needs to be considered and optimized for the best use of silicon carbide semiconductors. And as Professor Bhattacharya said before, this is a must. We have to do it. We are forced to do it with silicon carbide. The one-to-one replacement will not work. In addition, I will ask you a question. If we have the same system with silicon IGBTs, we take the silicon IGBTs out and we connect or we install more expensive silicon carbide semiconductors, and we operate the same system, what we will get? Maybe efficiency increment, okay. But for that, we would have to be switching very fast. If the system is not optimized for fast switching, we will have to slow down our devices. So we would end up with exactly the same performance as silicon IGBTs, but a higher cost. So if we optimize the whole system, reducing the filters, increasing the switching frequency, taking full advantage of silicon carbide semiconductors, we would be able to reduce the cost in the peripherals or other components, take full advantage of silicon carbide, and maybe compensate the extra cost used in the semiconductors. And again, we can use the better switching characteristics of silicon carbide to implement more simple topologies. So in applications in where 3-level topologies are needed nowadays, in order to keep a high efficiency, for example, we can use silicon carbide semiconductors in 2-level topologies, simplifying the power stage. Remember, we can measure short loops with only one module with the impedance analyzers. It's more simple. We have less component count, so it will be more cost effective, and still we would be able to increase the efficiency of our 3-level silicon counterpart. However, there is still several technical work to be done in order to be able to fully use the silicon carbide switching characteristics. So related to that future work, I divide, or in my mind, this work is divided in 2 main topics. The first one is related to the application level. We have to analyze the real impact of silicon carbide semiconductors in real applications. For that, we can use, for example, the LCOE metric used in energy sources. However, we have to combine technical characteristics, technical parameters, such as efficiency, switching frequency, and so on, with economical variables, such as the cost of the whole system, the cost of the filters, maybe commercial indicators, the development risk, or the time to market, these kind of parameters. The failure rate also. So we have to analyze the whole system using metrics such as the LCOE. Then if we classify these applications with all the data included, maybe we can find some similar characteristics in the applications that are benefiting the most out of the silicon carbides, and we can deduce that maybe long distance, high speed trains can benefit more out of silicon carbide switching characteristics than urban metros, for example, or totally the opposite, that urban buses, electric buses, can benefit more out of the silicon carbide devices than long distance buses at application level. If we focus at semiconductor level, we have to define a method to calculate the safe switching area of these semiconductors. For a given system, for a given topology, semiconductor, and power stage system, we have to be able to predict the maximum safe DVDT and DIDT before the destructive phenomena appear. Doing so, we would be able to use the full switching benefits of the silicon carbide. However, in order to be able to predict this maximum DVDT and DIDT, we have to be able to develop reliable but simple models to predict accurately the destructive phenomenon. We have to be able to measure the parasitic components in our power stage accurately. And of course, we have to develop accurate voltage and current measurements for high power in order to correctly analyze the waveforms of our power stage. So again, as Professor Aispuru said, the measurement systems and equipment should keep up with the development of the semiconductors and power stages. These are the references that I showed in during this presentation. And now I'm open to answer all your questions. Thank you very much.
Thank you. Nice presentation. Do we have any question in the audience? No questions? You have done nice. Okay. So thank you, Anton.
Thank you, Miguel.
Working here, microphone. Okay, now. So we have come to the last speaker, Dr. Jon Anzola, who will talk about the partial power converters in DC-DC applications, as Anton said, okay? Dr. Jon Anzola received the bachelor, master, and PhD degrees, all of them from Mondragon Unibertsitatea. He currently works as a lecturer and researcher in Mondragon in the topic of power electronics. His current research interests include modeling of power converters, partial power processing-based architectures, and power converters for hydrogen generation applications. He has published 3 JCR journal articles and over 10 conference publications. Please, John, the floor is yours.
Thank you. So is it okay? Yeah, okay. Well, for those who don't know me, my name is Jon Anzola Garcia, and today I will talk about partial power converters for DC-DC applications. Well, the main objective of this presentation is to present you the idea of the topic of partial power processing, the benefits it presents, and also the main contributions we have achieved through this PhD and the main conclusions also that we obtained. So as introduction, as Anton presented, well, regarding the efficiency plans we have to improve power converters, there are great efforts being made to improve their performance. I will focus on DC-DC converters where we can find different type of solutions to improve their performance. At component level, as we have discussed in this workshop, we have the new wide bandgap devices like silicon carbide and gallium nitride that are promising solutions for reduction of power losses of semiconductors. But also we can observe how different articles try to improve the performance and reduce the size of passive components like magnetics and capacitors. And then at system level, it's where we find well, new topologies, for example, based in resonant tanks that seek for soft switching conditions in order to improve the performance of the power converter. And then at the architecture level, it's where we find partial power processing, where I will focus in this presentation. So in order to understand the idea of partial power processing, I always make the same question. Imagine that a load consumes 1 kilowatt. Is it really necessary that the power converter in charge of supplying power to this load must process the full kilowatt, the full power of the application? Well, this is what we have assumed until now, and it's known as full power processing, where the power processed by the converter, it's all the power of the application, all the power that flows from the source to the load. However, there is an alternative known as partial power processing, where the power processed by the converter is just a small fraction of the total power. And in this type of solutions, the efficiency of the converter and the efficiency of the system are 2 different parameters. However, they are related by the KPR, or also known as the partial power ratio, the division between the power processed by the converter and the power of the system. So when we are working with partial power processing based converters, it's very important to differentiate the parameters of the converter, which would be the input and output voltage, current, and power, and the parameters of the system, the source and load, voltage, current, and power. So when we started with this PhD, we had a very clear objective, and it was to demonstrate or to improve the performance of a DC-DC converter through partial power processing. And with this, what we expect to improve is not only achieving a smaller size solution, but also with higher efficiency and reduced cost. What we expect through the implementation of partial power processing, it's an improvement in different metrics. So, well, the first step in all the PhDs, it's the same. It's to review the state of the art, to understand and to read about what has been done until now. And here we were able to classify 3 different strategies for achieving partial power processing. The first one are the differential power converters, or DPCs, very focused on a specific application where you have series connected elements like battery cells. Some of them can be more discharged than others. So in order to not consume the same current by all of them, you implement this type of DPCs to correct that current mismatch. And you only process the mismatch between the series connected elements. Then we have the partial power converters, or PPCs, typical application where you have a source, a load, the converter in between, and this converter will only process a small fraction of the total power. And then the mixed strategies, which could be hybrid solutions between DPCs and PPCs, and they can present a better performance at specific applications. However, well, I will focus on partial power converters, which are the type of solutions that we have focused on due to their numerous applications. And here we can observe in the literature 2 different architectures or solutions. The IPOS ISOP type architectures, also known as input parallel output series or input series output parallel, that require the implementation of isolated topologies in order to avoid a short circuit of the source or the load. So it's a must. We are obliged to implement isolated topologies. And then we have the fractional charging converters that enable the implementation of non-isolated topologies like the buck or the boost, which usually require a less number of semiconductors than the isolated ones. So if we start analyzing the IPOS ISOP type architectures in the literature, we can find different type of solutions with different namings, but applying Kirchhoff's laws, it is very simple to express or define the KPR, the partial power ratio, in function of the efficiency of the system, which we will consider as ideal, as 1, and the voltage gain of the application, the division between the load voltage and the source voltage. So if we compute the KPR for all of these architectures, we obtain the next figure, where 2 conclusions can be obtained. The first one, the closer the GV, the voltage gain, is to 1, the lower the value of KPR. This means that the closer the low voltage and the source voltage are between them, the lower power will be processed by the converter. And this repeats in all the architectures. First conclusion. And second, all the architectures presented in the literature can be represented by only 2. The IPOS step up, ideal for boost applications, and the ISOP step down, ideal for buck applications. If the application requires buck and boost functionalities, they can be implemented, but the selection of the ideal solution requires a more extensive analysis. And on the other hand, we have the fractional charging types converters. Also, we have ideal for a step up and ideal for a step down. Compared to the IPOS ISOP type solutions, they allow the implementation of non-isolated topologies, simpler solutions than the isolated ones, but they have a drawback, and they have a limited application range. If the voltage gain of the application is below 0.5 or above 2, the KPR it's higher than 1, and all the benefits of partial power processing are lost. So if we compare both solutions, we can conclude that the first one achieves a lower KPR. The power processed by the converter in an IPOS ISOP type architecture, it's going to be lower, but they require more complex topologies. However, the FCC type architectures, they allow the implementation of non-isolated topologies, but they have a limited operation range. So in order to sum up the main benefits of partial power converters, well, the first one, it's pretty obvious. The power processed by the converter is going to be reduced. So we can expect a smaller volume solution with higher efficiency, or at least achieving a higher efficiency should not be that complicated. And then we are able to implement lower current voltage class devices inside the power converter, which can lead to a lower cost solution. Regarding the drawbacks, both solutions, the IPOS ISOP type architectures and the FCC type, they do not provide galvanic isolation. So if the application requires isolation, they cannot be implemented. On the other hand, due to the implementation of lower current voltage class devices, there is a higher risk of provoking overvoltages at startup conditions, for example. We know that there is a voltage gain dependency. If the application consists of a high step up or high step down, the power or the reduction of the power processed by the converter is not going to be that remarkable. And finally, imagine the next application in which you have a variable low voltage and a constant source. A full power converter will observe always a constant input voltage and a variable output voltage. However, in a partial power converter, not only the output will be variable in function of the low voltage, but also the input will be affected. So this will affect to the design of the power converter because it will be required for a wider operation range. And well, this is a drawback. So in this presentation, I will try to also, as I mentioned before, conclude present the main conclusions and that we observe in this PhD. Regarding the FCC type architectures, remember the ones that enable the implementation of non-isolated topologies. Here, our main objective was to demonstrate that a non-isolated topology implemented in a FCC type architecture can outperform its full power counterpart. And for this case study, we analyzed two different non-isolated topologies. The conventional, very well-known half bridge with two semiconductors and a single inductor, and the modified switch inductor boost converter, which contains 5 semiconductors and double inductor. For this case study, what we did was to compare the performance between a half bridge implemented in a full power converter architecture against the half bridge implemented in a partial power converter architecture. Here, what we concluded was that identical results were obtained in both solutions. There was no improvement when implementing the half bridge in a PPC architecture. It wasn't worse, but it was the same result, same steady state waveforms and similar efficiencies than the half bridge full power converter. However, regarding the MSIVC, we follow the same procedure. We compare the performance of the full power converter against the partial power converter. And here, we did observe a lower inductor current, but a higher inductor current in the output capacitor. But in overall, the system efficiency improved when the MSIVC was implemented in a FCC type, FCC type architecture. So we did contribute to the literature by demonstrating that certain non-isolated topologies like the MSIVC can present a better performance when they are implemented in a PPC architecture. However, we still had some doubts about the real benefits of this solution because the MSIVC PPC, although it outperformed its full power counterpart, it didn't outperform the performance of a half bridge full power converter, especially for two reasons. We must implement a higher number of semiconductors, like 5 semiconductors and double inductor. And also in the experimental tests, we did observe higher over temperatures of the devices. So we decided to end here the analysis. We suggest for such additional non-isolated topologies that they improve the performance in FCC type architectures, but not only that, also that they outperform the half bridge full power converter. So then what we decided was to go for the analysis of IPOS, ISOP type architectures that do require the implementation of isolated topologies. And here, well, we developed different case studies, but the main one I will present here was the comparison of an isolated topology, in this case, a dual active bridge, implemented in an ISOP architecture, and compare its performance against a non-isolated full power converter. In the literature, it's very common to observe the comparison between an isolated topology implemented in a PPC architecture and compare its performance against its full power counterpart. However, there you are comparing an isolated solution with a non-isolated one. And in our opinion, an ISOP type architecture should be compared against a non-isolated full power converter. And this is what we did in this case study. So if we go into the analysis, we went for the comparison between these two solutions, where we established two constraints. We decided to maintain the same number of semiconductors in both solutions. So bearing in mind that the dual active bridge requires 8 semiconductors, we connected 4 half-bridge converters in parallel in order to have the same number of semiconductors. And also regarding the switching frequency of the semiconductors, we define it to achieve the same frequency seen by the output capacitor. And regarding the test conditions, we decided to compare the performance in 4 test points, where the source voltage and the low voltage are kept constant, and the only parameter that we varied is the low voltage that we increase from 225 volts up to 295. As you can observe in this voltage increment, the voltage gain gets closer to 1 because we are getting closer to the 300. So the KPR decreases and the power processed by the dual active bridge decreases from test point 1 to test point 4. This is important to understand the next results. If we focus in the system efficiency, here the blue line, which represents the efficiency of the interleaf half-bridge full power converter, at test point 1 and test point 2, we can observe that it presents a higher efficiency than the dual active bridge partial power converter, especially due to the low RMS current of the devices. However, as we go into test point 3 and test point 4, the power processed by the partial power converter is reduced, its efficiency increases, and it outperforms the efficiency of a non-isolated full power converter. So we demonstrated that at low KPR conditions, when the low voltage and the source voltage are very close to each other, a partial power converter can outperform a non-isolated full power converter. A very simple solution in this case, the interleaf half-bridge. So as main conclusion, we did also observe that the dual active bridge partial power converter require a smaller volume of the magnetics, to be more precise, 12% less. Similar overall efficiency was achieved. Still, the interleaf half-bridge presented higher results, but we did conclude that at low KPR conditions, the dual active bridge partial power converter can outperform, in this case, the interleaf half-bridge full power converter. Also, we observed a very different heat distribution. In the case of the half-bridge, the losses and the hotspots were distributed through all the branches. However, in the dual active bridge partial power converter, they were concentrated in the high current side, which was the primary side. And this could be beneficial from the point of view of the cooling system, to having concentrated in a specific place the losses or the heat. And finally, except for the output capacitor, we observed that the devices presented a lower electrical stress when they are implemented in a partial power converter. So we did conclude that partial power converters can outperform a non-isolated full power converter in different metrics. And finally, we wanted to demonstrate that all the benefits we were observing at downscale prototypes were also scalable to high power applications, that the benefits of partial power processing can be also observed in high power applications. And here we set to ourselves 2 objectives. The first one, since we know that the converter will not process all the power of the converter, all the power of the system, sorry, we decided to implement discrete type switching devices based on silicon technology for a high power application, which usually it's very common to observe the implementation of module type, even silicon carbide technologies. And the second objective was to design the converter in a way in which it could fit in the standardized enclosure, like a 4U rack box you see there. Here, the application that we considered was an electric vehicle fast charging application, where the DC-DC converter is located between a constant DC bus, what we assume as constant, and a variable load, which would be the battery of the electric vehicle, which we decided to model as this voltage profile you observe there. Here, we decided to limit the operation range between a 10% SOC and a 90% SOC, very typical in this type of applications, which benefits the partial power converter, especially because of this flat voltage we can observe in the battery profile. Also, we decided to establish the voltage DC bus at 800 volts, and we set to ourselves the objective of being capable of transferring up to 50 kilowatts. Here you can see an image of the arrangement we have done here in the university regarding the high power partial power converter, where we did not only design the arrangement of the devices, but also we enabled for AC grid connection for the power supply, manual switches to turn on, turn off the power supplies, and CAN and USB ports for connecting, for being able to connect with the DSP. And regarding the most interesting theme from this presentation, the experimental results we got at 50 kilowatts. Well, regarding the test conditions based on the nominal operation range, we set 5 different working conditions based on this profile, and we obtained the next results. We maintained an efficiency above 99% through all the operation range for a 50 kilowatt application with silicon technology. And as you can observe, the efficiency increases as the battery charges. Why is this? It's very simple. As the battery voltage increases, it gets closer to the 800 volts. The power processed by the dual active bridge partial power converter decreases, and therefore the efficiency improves. Well, I would also like to mention that testing at 800 volts and 50 kilowatt application here in the university entails a real challenge equipment-wise. And as we have discussed in this presentation, we decided to build a second converter in order to achieve an energy ring, making both converters to process the power in opposite directions. And this way, what we achieved was to make the equipment used for source or load only see the power losses of both converters, not the 50 kilowatts that we were transferring from one side to another. And then regarding the top case temperature of the devices, the most critical ones were located in the primary side, but still very low temperatures were achieved, below 45 degrees. So we decided to go an extra analysis to an overboost capacity, where we wanted to observe the maximum power that could be transferred with this converter. So we established the phase shift at 90 degrees, and we were capable to transfer up to 60 kilowatts, still with a very high efficiency, above 99%, and still with very low top case temperature of the devices, which gives room for improvement in this design. Also, well, I mentioned that we established the nominal operation range in between 10% SOC and 90% SOC, but we wanted to observe the performance of a partial power converter outside this operation range. So we established 4 test points below 10% SOC and above 90% SOC, achieving the next results. We did observe that below 10% SOC, as the voltage drop of the battery profile goes down, it affects negatively to the performance of the partial power converter. It must process higher power and its efficiency drops down dramatically. However, above 90% SOC, efficiencies above 99% are ensured and no major problems are observed. So as main results, we did contributed by presenting a design of a partial power converter for a 50 kilowatt application based on silicon technology and discrete switching devices. Still, the efficiency was not affected. We have maintained an efficiency above 99% through all the operation range. We are capable to transfer up to a peak value above 60 kilowatts, more than the one we designed for. The low thermal stress also gives room for improvement of the design. Maybe we could even decrease the size of the heat sinks. And also the prototype is validated for not only the nominal operation range, but also outside. It can work there. So as main conclusions, regarding the FCC type architectures, we demonstrated that non-isolated topologies can achieve partial power processing when they are implemented in FCC type architectures, but still further research must be carried out in order to observe the real benefits of this type of solutions. And regarding the ISOP type architectures, the ones, in my opinion, the most promising ones, we have observed that a partial power converter, in this case a dual active bridge, can outperform a non-isolated full power converter in certain metrics, like smaller volume of magnetics, lower electrical stress, and efficiency-wise also, if the application it consists of a very low voltage gain, at low KPR conditions, we can improve the performance of a non-isolated full power converter. And finally, regarding the high power PPC, we have validated a converter, a 50 kilowatt partial power converter with silicon-based technology and discrete switching devices, which is a breakthrough in the literature. Still, efficiency is maintained above 99% and a reduced top case of temperature of the switching devices. So here it ends the presentation. Thank you very much for listening. And if there are any questions.
Okay. Is there any question regarding the partial power converters for John? No questions?
Okay, better.
No questions in the chat? Okay, so thank you,
Miguel.
John, for your presentation.
So it seems we just have come to the end of this event just in time, as expected. Well, you see, we have seen very diverse presentations, lots of different topics, but all of them are power electronics, different applications, different voltage levels, power levels. But I said all of them are power electronics, and they will contribute to in this energy transition. Okay, thank you everybody for coming to our place. Also those that have been online, if they are still there. It's been a pleasure for us to have you all here. Okay. Thanks especially for the speakers, Michael, Professor Andersen, Professor Tolbert, my colleagues Josu and John, Igor, I don't know where are you, yeah, Professor Bhattacharya. Thank you especially for you for coming from so far. It's been really, really interesting for us to have you here, okay?